Hi everyone, so we have started studying about antenna, and in the last lecture, in the very last, we saw that we are going to study about three kind of antenna: Hertzian dipole antenna, where the length is very small, and large dipole antenna, where the length is greater than lambda by 10, and then length is in between. So now we are going to study about Hertzian dipole antenna. So length is very small. How small? That your length is less than lambda by 50. Your length is less than lambda by 50. Look, the length is very small, no? Since the length is very small, sometimes the length of Hertzian dipole antenna is shown by dl. Here dl is not the small portion that we are taking. No, dl is the length of Hertzian dipole antenna only. Since it is very small, that's why we are showing it as dl, because length is very small. So somewhere, let's just say in the question it is given that the length of Hertzian dipole antenna is 100 by lambda by 100. The length that is given is lambda by 100. So value of dl is lambda by 100. Okay, so since the length is pretty small, sometimes it is shown by dl only. So what is dl? This is your dl. So this is our Hertzian dipole at point P. At point P, we need to find the expression of E field. We need to find the expression of H field. When we have E field and H field, what we are going to find? At the point P, we will find the expression of E field. We will find the expression of H field. Once we have E and H, can I find the P average? Yes, because what is P average? 1 by 2 real of ES cross HS conjugate, right? And if I have P average, can I find P radiated? Power radiated. What will be power radiated? P average dot ds. So our final goal is to find how much power this antenna can radiate. What is our final goal? Our final goal is to find how much power this antenna can radiate. This is our final goal. Well and good. So how we will start? We need to find EH, then we need to find P average, and then we need to find P radiated. Now, how you can find H? You can find H with the help of E, right? You can find H with the help of A. What is A? A is the magnetic vector potential. Del cross A is equals to mu H. So from there you can find your H as well. So magnetic vector potential we will find, then we can find H. With the help of H we can find E as well, then P average. So this process we are going to see. Now path is clear, right? What is the path? We need to get to P radiated. This is our path. Now here we will be requiring an angle that is theta. What is this theta? So theta is the angle that we studied in our spherical coordinate system. So this theta is known as azimuthal angle. Okay, this is known as azimuthal angle. So this theta is the azimuthal angle that is measured from z axis. So theta is the angle that is measured from z axis. Now what is theta here? Here theta is not azimuthal angle. Here the theta is the angle between the arms of antenna and AR vector. This is your R. This is your R, right? What is R? R is the distance from the antenna to the point P where we are finding all the parameters. Like we will find magnetic vector potential, we will find their E field, H field, all these points we will find. So from antenna at distance R there is a point P. So in which direction the point P is there? In the AR cap direction. In the AR cap direction. So what is your theta? Theta is the angle between arms of antenna and AR cap. Are you getting this point? Theta is the angle between arm of antenna and AR cap. Okay, let me make it better. This AR cap I could have made it better. This would be your AR cap. A very important point. What is theta? Theta is not the azimuthal angle. It is the angle between the arms of antenna and AR cap. Luckily here it is equals to azimuthal angle only. Why it is equals to azimuthal angle? Because what is azimuthal angle? Azimuthal angle is the angle measured from z axis towards the direction of R. If you see this diagram, so what is your azimuthal angle? Here azimuthal angle is the same thing, no? Measured from z axis towards the direction of R. That is your theta. So a very important point. When we define theta, we are defining that angle between the arms of antenna and AR cap. Here for this geometry, for this particular geometry, our theta is equals to azimuthal angle only. Both angles are same. Whether you call it angle between the arm of antenna and AR cap, or you call it azimuthal angle, both are the same thing. Are you getting this point? But not necessarily they will be same. Always it is not necessary that they will be same. We will frame a question where both things will be different. So as of now, you can remember theta as azimuthal angle only, but always remember what is your theta. Theta is the angle between the arms of antenna and AR cap, and this is the point a lot of students miss. They always think that theta is azimuthal angle, and in all the formula they will put this theta only, but not necessary this theta will be put everywhere. We will frame a question where some things will be different. So at that time I will explain you this point again. So did you understand the meaning of theta here? Okay, theta is also clear, path is also clear. What we need to find? We need to find P radiated. So for that, what all things we will find, that also is clear to you. Now one more thing. So this is your Hertzian dipole. The length is very less. The length is very small, which is less than lambda by 50. Now this is your standing wave pattern. No? This is your standing wave pattern of current. Like here at this point you will have current minima. So if I call this point as, let's just say this point is my 0 0 0. This point is my 0 0 0. This origin is 0 0 0. Can I call this point as 0 0 dl by 2? Say yes or no? Because this complete length is dl. If this point is 0 0 0, so this length will be dl by 2. So can I call this point as 0 0 dl by 2? And what about this point? Can I call this point as 0 0 minus dl by 2? Right? So what is this? What is this point? This point is minus, sorry, not minus. This point is dl by 2. At dl by 2 you are having minima. At dl by 2 you are having current minima, and then you work here. Then you work in this direction. So this will be dl by 2 plus lambda by 4. What about this point? This point will be dl by 2 plus lambda by 2, and then you will work in this direction. Now this complete dl is very less than, this complete dl is less than lambda by 50. Let's just say my dl is lambda by 100. Lambda by 100 is less than lambda by 50. So how much dl length will be there? Like if you show it on this particular graph, then how much dl length will be there? Like it will be very small. This much distance is lambda by 4. Now I need to show lambda by 100 on this graph. What I need to show? I need to show lambda by 100 on this graph, and this length is lambda by 4 and lambda by 100. So that will be very small, no? Are you getting this point? Here initially you are having current minima. Initially you are having some current, but not necessarily the current will always be same. Like these waveform will keep on moving, right? From up to down, up to down. These waveform will keep on moving. So current here will change. But the thing is, the current will always be uniform here. On the arms of antenna, the current will be always uniform, because this particular portion is very less. And although this is sinusoid, although the waveform is sinusoid, but since the portion is very less, so this amount of current will change by very minute amount. What I mean to say is that, what is the value of sine 0 degree? 0 only. Or if I write down sine beta into 0 degree, that will be 0 degree only. And now if I ask you the value of sine beta lambda by 100, what that value will be? That will also be nearly around 0 only, because what is beta? Beta is 2 pi by lambda into lambda by 100, so that would be lambda by 50. So sine and that would be pi by 50. So what I am asking is that sine 0 is 0, sine pi by 50 is also nearly around 0 only. Are you getting this point? What I mean to say is that if these values are changing very less, let us say here there is some x value, now it has changed to x plus lambda by 100. So the value of here, the value of your current did not change much. Are you getting this point? The value of current did not change much. So the current on the arms of Hertzian dipole is uniform. You will not say it is constant. Why you cannot say it is constant? Because current will keep on changing, no? At this time this is the magnitude, but after some time this magnitude will come down. So magnitude will change, then it will again go up. So magnitude will keep on changing, but certainly it will be uniform. Uniform means it will not be a function of space. That means with the space, even if you are here, or 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 you are here. So on the arms of antenna, you will find the same amount of current. If I say here the current is 5 ampere, so here also the current will be 5 ampere, here also the current will be 5 ampere, here also the current will be 5 ampere, here also 5 ampere, 5 ampere. The current will change by a very minute amount. Why is that so? Because current is changing as per sinusoid, and in this range of lambda by 100, in this range of lambda by 100, the current will change by a very minute amount. So if here there is 5 ampere current, here also there will be 5 ampere, 5 ampere, 5 ampere. I am not sure the current will always be 5 ampere. Current can change. What I mean to say is that current can go from 5 ampere to minus 5 ampere as well. But if the current has gone to minus 5 ampere at this point, then here as well it will be minus 5, 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 here also minus 5, here also minus 5. What I mean to say is that on the arms of antenna, the current will always be same, or you can say uniform. What do you mean by uniform? Uniform means it is not a function of space. It is not a function of space. What does that mean? That it is not changing with respect to the length. So on the complete length, the current will always be same. If at this point, if at this point you are having I naught, then here also there is I naught, here also I naught, here also I naught, here also I naught. Are you getting this point or not? So sometimes in the statement it can be written that there is an antenna who is having uniform current on its arm. They will not mention the length. They will not mention the length. In the statement, if it is written that on the length of the antenna, the current is uniform, that means certainly they are talking about Hertzian dipole. Are you getting this point? Let's just say if the length was lambda by 2. If the length was lambda by 2. From here to here, the length was lambda by 2. Then what would be the lambda by 2? This much length will be lambda by 2, right? This much length will be lambda by 2. So from here to here, the length is lambda by 2. So now the current value will be a function of space, because at this point you will be having 0 current. At this point you will be having this current, at this point you will be having 0 current, somewhere in between you will be having this current, then this current, then this current. Then that would be a function of space. But now the length is so small that current value is not even changing. Are you getting this point? So this is a very important point. The same point we are going to write down in our other antennas as well. But as of now in Hertzian dipole, what you have understood, that in Hertzian dipole the current is not a function of space. That means current is uniform. So what we can keep, this we can remove. This is dl plus lambda by 4, this is dl plus lambda by 2, this length, okay, this we can ignore, this we can ignore. This is a very small length which I need to show. And like this was the standing wave pattern. Why I have made these two, did you understand? This is the actual wave and this is the standing wave pattern, because in standing wave pattern we always show the magnitude. That's why I made these two. Otherwise you can ignore this. Okay, you can ignore this. You can consider the wave is like this only. But when we make the standing wave pattern, then I will show magnitude of this one. So this is how I make it. Right? So you can keep in this manner. And then so I hope the point is clear. The point is that till now what we have seen, this was our Hertzian dipole, which is Hertzian dipole antenna, which is placed along z-axis. Arms is placed along z-axis. At point P we need to find certain things. We are having an angle of theta which is made from z-axis. So, and the definition of theta is here is that it is the angle between the AR cap and the arms of our dipole antenna. This is the arm of our dipole antenna and this is the AR vector. So this is our theta. Is that clear to you? So this is the theta we are using. And rest all things angle between the arms of antenna, this is our theta. And then we go to know what we got to know. We got to know that on the arms of Hertzian dipole, the current distribution is uniform. Uniform means not a function of space. Not a function of space. So if I ask you at a particular time, at this point your current is 5 ampere. Then at that time only what will be the current at this point? You will say, sir, it is 5 ampere only. If I say at a particular instant of time, the current at this point is 3 ampere, then what will be the current at this point? That will also be 3 ampere only. At some particular instant of time, the current here is 2 ampere, then what will be the current at this point? That will also be 2 ampere only. On the arms of antenna, the current will be uniform. Why is that so? Because length is very small, and since the length is very small, so current will not change much. Are you getting this point? Is that clear to you? Well and good. And what is our target? So this target also I have written down. We need to find the power radiated by the antenna. What is our target? Final target is we need to find this. How we can find? First we will find the magnetic vector potential. That I have already told you how to write down the magnetic vector potential. Then I will find HS from there, because I know that del cross A is equals to mu H. So from there what will be your HS? Del cross A is divided by mu. And if I have H, then can I find out E? Yes, using Maxwell equation. Del cross H is equals to j omega mu epsilon Es. So this Maxwell equation, do you remember? Certainly you remember. So what do you get? Del cross Hs divided by j omega epsilon. What was this equation actually? Do you remember? This was your modified Ampere's law. Here we have considered sigma equals to 0. Okay. No conductivity is there. Sigma equals to 0. So the medium that we are going to use, that will be non-conducting. It would be perfect dielectric, or you can say free space. So sigma equals to 0 we will consider always. So if I know Hs, can I find out Es? Del cross H divided by j omega epsilon. And then I can find out my P average, and from there I can find out P radiated. So this target is also clear. So till now we did not understand anything new in this slide, but very important things we have understood, that our current distribution will be uniform, and theta is the angle between the arms of antenna and AR cap. Okay. So let's write down the magnetic vector potential. Again, a very important point is about to come. So this is Z axis, X axis and Y axis, and this is our Hertzian dipole antenna. Now I have shown it by a simple line. So a kind of wire I have shown, because this is very small, no? This is very small. The dipole antenna is very small. So you can take it as a point source only, no? Since the length is very small, so kind of point source you can take it. It is a point source only. Hertzian dipole is a kind of point source only, because the length is very small. Say yes or no? And if there is a point source, then how do you solve the geometry of that point source? Let's just say, because of the point source, I ask you what is the electric field at a certain point. So that will be solved using spherical coordinate system. As a ECE student, we did not study about electrostats and magnostats, right? There is a portion of EMFT, that is electrostats and magnostats, that is in the electrical syllabus, that is not in our ECE syllabus. So that we did not study. So there it is told that whenever there is a point charge or anything that is point, so there you need to use spherical coordinate system. So this is also a point charge only, you know? It is like a point source only. Although it is like this is not a point, but the length is so small that you can consider it as a point source only. So that's why we need to use spherical coordinate system. So here we are going to use spherical coordinate system. So that only I have drawn, that making an angle of theta with respect to Z axis, we are at point P, and at point P we need to find our magnetic vector potential. Okay. Here theta is the azimuthal angle, but this theta is azimuthal angle, but actually our theta is defined as the angle between the arms of antenna to the AR vector. So that is the theta, but that theta is luckily equals to azimuthal angle, but always it is not necessary that it will be equals to azimuthal angle. We will frame a problem, there we will see it is not equals to that, right? And the current that is flowing is I naught cos omega t. So I need to write down my dA vector at point P. What that would be? Do you remember the formula? That is mu ideal upon 4 pi r ideal. Here instead of I will write bracket I. I will tell you the meaning of this one. Okay. What is this? This is your bracket I. This is known as retarded current function. Retarded current function. What is the meaning of this bracket I? That I will tell you. So what I have written, dA is mu ideal 4 pi r. Okay. Now what is this retarded current function? So this is your wire, and at some point P you are finding magnetic vector potential because of this wire. Why this magnetic vector potential is coming into action? Because of the current. Because of the current. Look, because of the current there is magnetic field. If there is magnetic field, that means there is H, and if there is H, that means there is A. Because if H is there, that means del cross A is equals to mu H. So if H is finite, then this A is also finite. If H is non-zero, then this A is also non-zero. So basically, if there is current, then there is B. If there is B, that means there is H. And if there is H, that means there is A. Now, from an antenna, if some waves are being radiated from this antenna, some waves are being irradiated, so that will take some time to reach at this point, no? If you remember the animation, if you remember our animation, so when the waves were generated, so it was taking some time, like from here the waves were generated, and it was taking some time to reach here. When the EM wave was generated, so it will take some time, no? Like this point is very far, this point P is very far, so it will take some time to reach there. Certainly it will take some time. So let's just say the wave was generated at some 7 seconds. At some 7 seconds the wave was generated. Now to cover from here to here, to cover this distance r, let's just say it is taking 5 second of time. After 5 seconds it reaches here. So it is reaching at 12 seconds. Now at 7 seconds, let's just say the current here was 5 ampere. At 7 seconds the current here was 5 ampere. So at 12 seconds, you are having the value of A. At 12 seconds you are having the value of A because of the current at 7 seconds. No? Are you getting this point? In this wire, the current at 7 seconds was something. That current was 5 ampere. Now, because of this current, the magnetic vector potential at this point will be reaching after 5 more seconds. That means it will be reaching at 12 seconds. So the magnetic vector potential at point P, you are writing down because of the current at 7 seconds. Although the magnetic vector potential you are getting here at 12 seconds, the potential you are getting here at 12 seconds, but you are writing down the current of 7 seconds. Are you getting this point or not? So some previous current you are writing, no. What I mean to say is that if I had written here the value of current, if I had written I naught cos omega t, then dl vector divided by 4 pi r, then that would be wrong. Why that would be wrong? Because if I write cos omega t, that means I am saying that whatever the current that was generated at time t, because of that current I am having the magnetic vector potential at point P. But no, the magnetic vector potential at P, if you are writing at time t, if you are writing down the magnetic vector potential at point P and you are saying that at time t this is the magnetic vector potential, so actually it is coming because of the current that was 5 seconds before. That means t minus 5 seconds. Similarly, what I said here is that at the time 7 seconds the current was 5 ampere, but this took time of 5 more seconds to reach here. That means at 12 seconds you are getting the value of magnetic vector potential because of this current of 5 ampere, and which was coming at 7 seconds. So there is that delay of 5 seconds, no, like this time it took. So if I am writing here, let's remove it off. I hope you got the point. So what current I should write now? What will be the value of my retarded current? So that is I naught cos omega t minus t naught, right? Because if I am writing down the magnetic vector potential at some time t, so that magnetic vector potential would be coming because of the current at a time t minus t naught. Here if I am writing down the magnetic vector potential at 12 seconds, that means it would be coming because of the current at 7 seconds, because it took 5 seconds of time. If I am writing down the magnetic vector potential at 12 seconds, that means that is coming because of the current at 7 seconds. So that means here if I am writing down the magnetic vector potential for 12 seconds, at 12 seconds, that means the time window that I need to put, that has to be 7 seconds. So here t is 12, t naught is 5. So 12 minus 5, that is 7 seconds. So what is t naught? T naught is the time that is taken by the wave to reach from here to here. What is t naught? T naught is the time that is taken by the wave to reach from here to here. Here t naught is our 5 seconds. A very important point which is highly misunderstood by the students. So now you must have understood that what is this retarded current function. Just a second. Yeah. So let's continue. So we were talking about this magnetic vector potential, and you got to know that what is your retarded current function. I hope you understood. So what will be our t naught? So I naught cos omega t minus, what will be your t naught? T naught is the time taken by the wave to reach from here to here. So what will be time? Time is equals to distance upon speed, r by vp. Distance upon speed, speed is phase velocity. So I naught cos omega t minus, what is this omega by vp? What is beta? Wait a second. Time क्या होता है भाई? Time is distance upon time. Yeah, so distance upon speed. Yeah, okay, no issue. Distance upon speed So what is omega? Omega is, sorry, what is beta? Beta is omega by Vp only, no? Vp is equals to omega by beta. So what is beta? Beta is equals to omega by Vp only. So what is this? This is beta only. So I naught cos omega t minus beta r. So this is the value of your retarded current function, which you can keep in mind directly. Say yes or no. Although this cos is coming because we have taken our current function to be cos. Here if you were taking sine, then here sine would be coming. This should be clear to you, right? Here cos is coming because here we have taken cos. It could be sine as well. If it was sine, then here we would be getting sine only. Are you getting this point? Yeah. Now which formula we are going to apply? These formula we are going to apply, right? So these are applicable only for the phasor form. This formula, all these are applicable for phasor form. So you need to take phasor form here. So what I need to take? I need to take phasor form. So phasor of this current also I need to take. Rest all are other values only. So what I need to take? Actually I need to take the phasor of the current. That would be I naught e to the power minus j beta r. I hope you know how to take phasor. A separate lecture is there talking about phasor form, and why do we solve problems when in phasors only? Why do we do the calculation in phasor? What is the advantage of that? So all these things have been discussed in a great manner, right? Again I cannot discuss it. So whenever you take phasor, that means you suppress the time term. So time term is gone, then e to the power minus j beta r only is left. So this is your IS value, retarded current function, phasor form of retarded current function, right? So can I write down my DAS? DAS, can I write it down in this manner? What is the phasor form? I naught e to the power minus j beta r divided by 4 pi r. What is your DL? DL, can I write it down in this manner? dz az cap. Say yes or no. Is that clear to you? Why did I write down dz az cap? Did you understand this point? Because DL value you can take in the direction of z only, no? And then az cap. Why az cap? Because what is the direction of current? Current is flowing in the z direction, that's why az cap. Current is flowing towards z direction, that's why az cap. So we have discussed about this DL in the last lecture, right? Now what I need to do? I need to find AS vector. What I need to find? I need to find AS vector. So what will be your AS? Integration you need to do. Here what you are going to do? Here you are going to do the integration. So which integration you will have to do? All these are constant. All these are constant. So only integration you need to do this one. So if you do the integration of dz, what does that mean? You need to write down the complete length. Dz integration means simply you are integrating a small portion that you are taking and then you integrate that. So what do you think? What will be the value of integration dz? That will be dl, because what is the complete length? What is the complete length of your Hertzian dipole? That is dl only, no? Because I told you the length of Hertzian dipole is shown as dl. So the complete length is dl only. Here I am writing down dz. That means I am taking a small portion in the direction of z. When I integrate, that means the complete length is dl. This is a very good confusion actually. In a lot of aspirants, this is a confusion that, sir, in the final expression we write down mu naught I dl 4 pi r e to the power minus j beta r az cap. So sir, does that mean this dl still we need to integrate? What is written is that AS vector is equals to mu I dl 4 pi r e to the power minus j beta r az cap. So now it feels like that dl has to be integrated. No, dl is the length that you are getting after the integration, because the length of the complete Hertzian dipole is dl only. So this is not the expression of DAS. No, this is the expression of AS only. And this dl is the complete length. This dl is not the small length that you have taken. The small length that you have taken is dz. And when you integrate that dz, you are getting dl. Are you getting this point? So when you integrate this, what you get? When you integrate this, you get your dl value, right? So this length is dl. All this is clear. This I can remove it off. And from here, I can write down that this is my AS expression. This should be there in your mind. What you are getting? Mu I naught e to the power minus j beta r 4 pi r, and then this is dl. So this is how I remember. Mu I naught dl 4 pi r e to the power minus j beta r, and in the direction of dl. What is the direction of dl? That is az cap, right? What is the expression of A? Mu I upon 4 pi r, right? mu I dl upon 4 pi r. And what is the direction of dl? The direction of dl is the, what is the direction of A? The direction of A is in the direction of dl. And what is the direction of dl? The direction of dl is same as the direction of current. So here what is my direction of current? That is in AZ gap. So what I will write down? For Hertzian dipole, my magnetic vector potential is mu I naught dl upon 4 pi r. Now I need to write down that. Along with that, phasor form will also come, e to the power minus j beta r. Why this is coming? Because of this thing, that you are writing down the magnetic vector potential at point P, which is far away. That means it will take some time to reach there. So that's why I need to subtract it. So that's why this phasor form will also come, and then direction I need to tell, which is same as the current direction. So if you remember this expression very directly, you will be able to write it down. Actually, I remember this expression. What I remember? Mu I dl upon 4 pi r. Now if I am writing for Hertzian dipole, so in place of I will write down I naught e to the power minus j beta r. Then I need to write down dl, which is dl only, and then what is the direction? That is AZ gap. So mu ideal 4 pi r e to the power minus j beta r. What is the I naught here? I naught is the peak current. I naught is the peak current of the current source. I naught is the peak current. So here I am not writing I. Here I am not writing I. I am writing I naught. Your I is I naught cos omega t. When you take the phasor form, this is becoming I naught e to the power minus j beta r. So here your I naught is the peak current. So every single thing you need to know when you are seeing the derivation. And all these things from here questions can be framed. That's why I am spending time here. If I see any point from there questions cannot be framed, I am never gonna spend time. Like if you are following the playlist right from the beginning, then you would know that we are not spending any time from where the questions will not be framed. But from here questions can be framed. That's why we are spending some time here. So I naught is the peak current of the source. Okay. Now this AZ gap can be written in this manner, because we need to write down the expression in spherical coordinate system, right? But this is not in the spherical coordinate system, because in the spherical coordinate system the point P is defined as r comma theta comma phi. So we need to write down in terms of spherical coordinate system. So what is AZ gap? Cos theta AR gap minus sin theta A theta gap. Have we seen it somewhere? Yes. Where we have seen it? Here. AZ gap is equals to cos theta AR gap minus sin theta A theta gap. So this is what we are getting. So this is your AS vector. This is your AS vector. So you don't need to remember this one. You need to remember this one. So here I am putting the star mark. That means you need to remember this one, not this one, because AZ gap directly you can write down. So these things should be in your mind. Is that clear to you or not? Right? AZ gap equals to cos theta AR gap minus sin theta A theta gap. This you can write down. How will you write down? What do you know? What is Z? Z is equals to R cos theta. This you know, no? R cos theta. Then you know I will have to make a matrix. Here what will come? R theta phi. Here what will come? AX, AY, AZ. Right? Z is equals to R cos theta. So here theta cos theta will come. Then what you need to do? You need to differentiate with respect to theta. So what you will get? Minus sin theta. In the last row you will get 0 only. So AZ gap is equals to cos theta AR gap minus sin theta A theta gap. That's it. Within seconds you will be able to write down. So from here you will write down AZ gap is equals to AR cos theta gap. Then cos theta will be differentiated. That would be minus sin theta. First thing is AR, then next is A theta. That's it. So in the examination, which I think they can ask, if they are asking the magnetic vector potential, they can ask in the direction of Z as well, or they can ask in the direction of R and theta as well. Will you be able to write it down? Yes, very easily. Directly I can write down this expression. I don't need to do all these calculations. Although this calculation was very easy, mu I naught 4 pi r dl gap, dl vector, then what is the calculation? This is the retarded current function. That is the important point. So what is the retarded current function? That is I naught e to the power minus j beta r. You know the process, how it came, and directly now you need to remember that this is my IS. There is a phase difference. That's it. Because it will take some time. It will take some time to reach from here to here. That's why this is I naught e to the power minus j beta r. And from here I am getting AS, and then I did this thing. Now what do I need? I need the expression of HX. So what I need to do? Curl divided by mu is equals to HS. So you will calculate the curl now. You will do it on your own if you want to calculate the curl. How will you calculate the curl? This is the formula. Which formula? This formula you can apply. Then you can find out the curl. Although it is not important, no one will ask you to do the curl operation. And then once you have the value of Hs, what you can do? From Hs, what we know? Del cross Es is equals to j omega mu del cross Hs, really sorry, del cross Hs is equals to j omega mu j omega epsilon Es. So from here Es you can find out, that would be del cross Hs divided by j omega epsilon, right? So this is the equation you will use. You will find Hs, then again you will take the curl, you will get Es, right? So Es can be a function of r theta phi and Hs can also be a function of r theta phi. So when you do the calculation, these are the results that you will be getting. No one will ask you to remember these results, neither you need to remember these results, nor you need to do this calculation. If you want to do, you can do it on your own. You can find Hs as well, you can find Es as well if you want to do this calculation. When you do this calculation, these will be the results you will be getting. So what you will find is that your H is there only in the direction of phi. That means HRS and H theta S is 0. So if you see Hs, so H is only having H phi S. H is only having H phi S A phi cap. This is your Hs. And when you see your Es, so Es you will find that in the direction of phi there is nothing, but in the direction of r you are getting ERS AR cap, and in the direction of theta also you are getting something, that is E theta S A theta cap. So these are the expressions you are getting. Now from these expressions, what you can conclude? So all these are 0, these are 0. So let's not talk about them. Let's only see the non-zero one, H phi, ER and E theta. So in H phi S, there is a magnetic field because of two components. One is this, one is this. So here you find that this component is same. I dl sin theta upon 4 pi, I know dl sin theta upon 4 pi e to the power minus j beta. These are same. What is the difference? This is the difference. That one component is coming because of beta by r. This j is only the phase, don't care about this j. So one component is coming because of beta by r, another component is coming because of 1 by r square. Here also in ERS there are two components. This guy and this guy is same. What is this neta? What is this neta? If you ask me, sir, what is this neta? So neta is under root mu upon epsilon. Intrinsic impedance. Neta is intrinsic impedance here. Okay. I know dl cos theta 4 pi, everything you know. What is theta, that also you know. I know dl, all this we have seen. New term is neta. So neta is intrinsic impedance. Okay. Now what do you see here? There are also two components. One is because of 1 by r square. One is because of 1 by beta r cube. Here there are three components. One is because of beta r, 1 by r square, 1 by beta r cube. So what do you think? What you can conclude from here? That this expression and this expression, they are the function of beta by r, 1 by r square and beta by r cube. Generally people remember that these are the function of 1 by r, 1 by r square, 1 by r cube. But no, this is really sorry, these are the function of 1 by beta r cube. But no, this is not we need to remember. Here multiply by beta, here nothing multiply, here beta is in denominator. So they are the function of beta by r, 1 by r square and 1 by beta r cube. Are you getting this point? So this also should be in your mind. Now you let me know one thing, if r is very large, so here there is some antenna. So what is our target? Our target will be that for a very far field, how much energy it is radiating. For a very far field, how much, far field means which is r is very large. So for a very far field, how much energy it is radiating, how much power it is radiating, what is the value of EM energy, how much EM wave it is how much EM wave is being propagated at a very far field. So if r is very large, then what will happen? These values will be very low, 1 by r square will be very low, 1 by r cube will be very low. Like this will also be very low, 1 by r is also very low, but these will be very low. Are you getting this point? If R is large, then this will be very low. This will also be very low. This will also be very low. This will also be very low, and this will also be very low. Only this term and this term will be left. Say yes or no. If R is very, very large, right? But how large? How do you define that? What should be the value of R? What I am saying, what should be the value of R such that you can ignore these guys and this guy as well? What should be the value of R? So how will you define that? So what I'm going to find? I'm going to find the point where the magnetic field and electric field are equal because of beta by R, because of 1 by R square, and because of 1 by beta R cube. What I mean to say is that H phi S at what value of R? At what value of R? There are two components of H phi S. One is because of this, other one is because of this. So at what value of R? This component is equal to this component. At what value of R? This component is equal to this component. And at what value of R? This component is equal to this component, and that is equal to this component. Are you able to understand this point? So at what value of R all these components are equal? This is what I need to find. So that will be my boundary. Are you getting this point? At what value of R all these components are equal? That will be my boundary. Let's just say that value of R is coming out to be some alpha. So if R is greater than alpha, then that is known as far field. If R is less than alpha, that means all these will be coming in action. And in the examination, always 100% chance is there that R will be greater than alpha will be asked. 100% I am saying. 100%. They will never ask any question for R less than alpha. Never ever. Only one question is given in Sadiku, that is in front of me only. That is asked on R very, very less than alpha. But in the examination, they will never ask it. Because if you need to know R very less than alpha, like if they ask for near field, then you need to know all these expressions, which is not practically possible. That you cannot remember all these expressions. Now you will say that, sir, we will derive it in the examination. So this is easy to derive. This you can write down very easily. But will you be able to do this curl operation? It will take a lot of time. So practically, like 100% chances is there that if they are asking question in the examination from these expressions, then they will ask for far field only. So my target is to find what is my far field. So for that, what I am going to do is that I am going to take all these components equal. So that will be my boundary. If my R is greater than that particular value, then that would be R field. Otherwise, it will be near field. Okay. So far field and near field I need to define. For that, what I am going to do is that I am going to find the value of R at which all these components are equal. So let's find that out. So what I need to do, I need to put beta by R is equal to 1 by R square. Here also it is 1 by R square. 1 by R square will be equal to 1 by beta R cube. So you can say beta by R is equal to 1 by R square is equal to 1 by beta R cube. So beta by R, because of 1 by R, beta by R, because of 1 by R square, simply 1 by R square, and because of 1 by R cube, 1 by beta R cube. Okay. So we need to equate it. You can either solve this equation or you can solve this equation. From both of the equation, you are getting two equations. What is that? Beta is equal to 1 by R. And if you solve these two equations, then also you are getting beta equals to 1 by R. And if you solve these two equations, if you solve these two guys, or if you solve these two guys, always you are getting the same thing. Beta is equal to 1 by R. So when I solve this equation, what I am getting? Beta is equal to 1 by R, or you can say R is equal to 1 by beta. R is equal to 1 by beta. And what is beta? Beta is 2 pi by lambda. 2 pi is nearly 6, right? 2 pi is nearly 6. So if R is greater than lambda by 6, that is your far field. And if R is less than lambda by 6, that is your near field. That's it. So from these expressions, you don't need to remember these expressions, but from these expressions we got a conclusion that how will you differentiate whether it is my far field or near field. So if the value of R is mentioned, you will check whether it is greater than lambda by 6. If it is greater than lambda by 6, then certainly it is far field. And if it is far field, then what you can do? Ignore this, ignore this, ignore this, ignore this, and ignore this. Only take beta by R in action. So if you are talking about far field, here in far field, only beta by R will be coming into action. But in near field, beta by R will be coming in action. 1 by R square will be coming in action. And 1 by beta R cube will also be coming in action. Question will be asked on this only. Is that clear to you? So it's been 45 minutes. I will take a break. Now in the next slide, what we are going to do, we are going to write down the expressions for far field. Expression for far field. And those expressions you need to keep in mind. So as of now, let's revise whatever that we have studied. We started with Hertzian dipole. Length is very less. And we got to know that on the arms of antenna, on the arms of Hertzian dipole, the current is uniform. Why so? Because length is pretty small, and in the small length there will be no fluctuation of current. If at the upper point you are having I naught, then on all the point you will be having I naught only. Then we need to write down the magnetic vector potential. Okay, why we need to write down the magnetic vector potential? Because we need to find P radiated. So all these steps we need to do. So first we wrote down the magnetic vector potential. Mu ideal upon 4 pi r, this is the formula that we have studied. But here the current we will write down, that is the retarded current function. Why is that so? Because at a certain time you will be writing down a magnetic vector potential. So that magnetic vector potential you would have got because of the current before some time. So that before some time current I need to write. So that current would be T minus T naught. So if I am getting the magnetic vector potential at 12 seconds, that means that magnetic vector potential would be there because of the current at 7 seconds, right? So that I need to write down. So I naught cos omega t minus beta r. So this is my retarded current function, that is I naught e to the power minus j beta r. Okay, so that expression I will put, which is very easy. And then which expression I am gonna get? This expression I am gonna get. This I need to remember. This is my magnetic vector potential because of the Hertzian dipole at some point P, which is r radius away. Radial distance is r. Radial distance r away from your Hertzian dipole, making an angle of theta with the arm of antenna. And then from there I can do curl operation Hs. From there I can do curl operation Es. Then these expression I will get. From here I get to know that these are the function of beta by r, 1 by r square, 1 by beta r cube. At far field I can ignore these components, which is of 1 by r square and 1 by beta r cube. But what is my far field? For that what I need to do? I need to equate all of them. And when I equate all of them, then I will get to know the point where the components are, all the components are equal. This component, this component, this component, this component, this component, all these components are equal. So at that point I need to know. So for that I go to know the value of r is equals to lambda by 6, nearly lambda by 6. So if r is greater than lambda by 6, that is known as far field. If r is less than lambda by 6, that is known as near field. So questions will be asked on this field only, that r is greater than lambda by 6. So now for far field we are going to write down the expressions. So this is your Hertzian dipole, this is the length, this is the r distance. Here the current is flowing, here I have written sin omega t, but I have taken cos omega t. So this is your I naught cos omega t. This current is I naught cos omega t. Okay. So at point P, which is at a distance r, so there I need to write down my E and H components. I have my A component. What is that A component? AS is mu I naught upon 4 pi r dl e to the power minus j beta, because the current is I naught e to the power minus j beta, I naught dl, and then the direction of current. What is the direction of current? That is AZ gap. AZ gap. This is my AS. Now I need to write down my H phi and E theta. So that I will write down after a break. So you can try writing. Now you see which components will be coming into action. ER will be gone, right? Only this component will be coming in action, and then this component will also be gone, and here this component will also be gone. So you write down the expression of H phi and E theta. Okay, and then you try to remember them. I will pause the video. I will take a break. You can also take a break, and then we will start writing E and H expression. Yeah, so welcome to the second half. Now what we need to write? We need to write down the E and H expression. So what will happen is that here if we see, if we ignore these factors, so this will be gone, this will be gone, this will be gone, this will be gone, and this will be gone. So now what you are left with? So ERS will be 0, right? ERS will be 0, E phi s is already 0. So now only E theta s will be remaining, and here only H phi s will be remaining. So what you are getting? I naught dl sin theta upon 4 pi r j beta e to the power minus j beta r. So this is how we write it. So you need to remember this expression. So your total H field, it is having only 5 component. It is having only 5 component. And here we are writing the phasor form, right? Here we are writing the phasor form only because there is no time term. So we are writing the phasor form. So if I write down the phasor form, H of S, that means H phi s. So now you need to remember this expression. So this is how I remember it. So I dl sine theta. This is the complete line I remember, ideal sine theta. Again and again if you say it, you will be able to remember it. Ideal sine theta upon 4 pi r, ideal sine theta upon 4 pi r, then j beta a to the power minus j beta r, a phi cap. Why a phi cap? Because this is the component which is in phi direction, so a phi cap. So anyway you need to remember it. There, if you make any trick or anyhow, you need to keep in mind. You will never forget this e to the power minus j beta r, because what does this represent? This represents that radiation is in r direction. The radiation is in r direction and your magnetic field is dancing in phi direction. What about a theta? What about e theta? So if you write down electric field component, that means only e theta will be left. Only e theta will be left because this will be gone, 1 by r square will be gone, 1 by beta r cube will also be gone. So what you are getting? Here only e theta as component is there. So what you are getting? Neta into all these things same. In EM wave propagation, did you study E equals to neta h? So same thing is applied here. Neta into this thing again, right? So neta into I naught dl sine theta upon 4 pi r j beta e to the power minus j beta r. Certainly direction will be different, no? So what is the direction? A theta gap. Or how I can write it? Neta, then mode of h phi s, and the direction is in theta. So what did you understand here? Here your radiation is in r direction. Here I will not say EM wave is propagated in r direction. No, the radiation is in r direction. Electric field is dancing in theta and magnetic field is dancing in the direction of phi. And all these are perpendicular to each other. Did you understand this point? For far field, for Hertzian dipole, E and H expression for far field we are writing down. So we got to know that the radiation is in r direction. The radiation is in r direction. Your electric field is dancing in theta cap and your magnetic field is dancing in phi cap. And can you let me know, is this equation correct? Because r, theta and phi. So you know this thing that your AR cap is equals to A theta cap cross A phi cap. A theta cross A phi is equals to AR cap. So are we able to satisfy it? Yes, certainly we are able to satisfy it. So what we can say is that my radiation is in the direction of R. Direction of AR cap. So my radiation is in the direction of AR cap, but my electric field is dancing in theta direction and my magnetic field is dancing in phi direction. And this also is being this also is true, because you know that the direction of EM wave propagation is equals to the cross product of electric field direction and magnetic field direction. K is equals to E cross H, that we study, right? So similar thing is happening here, but here you will not say EM wave, here you will say radiation. So radiation is in R direction where my electric field is in theta cap and my magnetic field is in phi cap. So these two expressions you need to remember anyhow. If you remember this one, then anywhere you are going to remember ES as well. So you only need to remember H phi S expression, and again we are going to write it. So eventually you are going to remember it. Okay, well and good. So let's write down the time average Poynting vector now. So what is our time average Poynting vector and why we are writing it? Because what we need to find? We need to find P radiated. And if we need to find P radiated, then what do we need? P average dot ds. So that's why we are writing it. Let me fix it once, just a second. Yeah, so what is your P average? P average is 1 by 2 real of ES cross HS conjugate, that you already know. And here, which component of E you are having? Theta. And which component of H you are having? Phi. So 1 by 2 real of. Do you remember the E expression? No, we generally remember the H phi expression. So what is E expression? Neta into I naught dl sin theta upon 4 pi r. I naught dl sin theta upon 4 pi r into j beta into e to the power minus j beta r a theta gap. Say yes or no? Will you be able to remember this? It is not that tough. Ideal sin theta 4 pi r. This j beta you can forget. What was the expression of AS? That was ideal 4 pi r e to the power minus j beta r, and this was in z direction. Forget about the direction, but this you will be able to remember, no? Ideal 4 pi r e to the power minus j beta r. Here extra term is sin theta, along with that j beta is also coming. So that is the extra term only. Just a second. Yeah, so what I was saying, only the extra term is sin theta and j beta. So in that manner you can keep in mind. Anyway you need to keep it in mind. Okay. I know dl sin theta upon 4 pi r, j beta e to the power minus j beta r, a theta gap. Again we will write it down. What is your h phi s component? That is I dl sin theta. I know dl sin theta upon 4 pi r j beta. But here what we are writing the conjugate. So j will be replaced with minus j. J will be replaced with minus j. E to the power minus j beta r. But we are writing the conjugate, so j will be replaced with minus j. And then what is the direction? That is your phi cap. Right? Now what do you see? This and this is getting cancelled. Minus j into j, that would be plus 1. Now what you are getting is that 1 by 2 real of neta into ideal sin theta 4 pi r. Ideal sin theta 4 pi r. अरे भाई, ideal sin theta 4 pi r into beta whole square, right? Ideal sin theta 4 pi r into beta whole square, and then a theta cross a phi. What is that? A theta cross a phi. What is that? AR cap. So this is some expression you are getting, and no one need to remember it. No one should remember it. This is some expression, you can simplify it more, but whatever the expression you get in the end, no one need to remember it. We only need to remember the expression of P radiated. So the final expression that I tell you, that you need to remember. So this P average we have got. Now what do you understand from this? What is the direction of P average? AR cap. And how you can verify it? Radiation is in R direction, no? When we were studying EM wave, so what was the direction of P average? That was arrow cap, or you can say AP cap. In the direction of propagation, always energy is propagated in the direction of propagation, no? Here, what is the direction of radiation? That is in the direction of R. So energy is propagated in the direction of R. So what I can write? Energy is being propagated. Here only direction is important. This magnitude is not important. Energy is being radiated, not propagated. I should write radiated. Energy is being radiated in the direction of AR cap. What could, and here I am writing real of this guy, real of this quantity. Is this completely real? I know it is real, dl is real, 4 pi r is real, sin theta is real, beta is real, and this is your AR cap. So do I need this sign? Here I am writing 1 by real. This is 1 by 2, sorry. 1 by 2. So do I need to write down this real? Because this is completely real, no? This was the imaginary part, e to the power minus j beta, this got cancelled. This was the imaginary part, minus j into j, that got 1. Minus j into j is 1. Because j into j is j square, that is minus 1 into 1, minus 1, that is plus 1. So that is 1, that is also gone. So this complete quantity is real only. So what you are getting? 1 by 2 neta into whatever this is. What do you think? What is this? Can I write it down this as h phi s square AR cap? Isn't it the magnitude of h phi? What is your h phi s? Don't look back. Write down h phi s expression on your own. The more you write down, the more you will be able to remember. So what is that expression? Ideal sin theta upon 4 pi r j beta e to the power minus j beta r a phi cap. And if you take the magnitude, this will be gone if I take the magnitude, this will be gone if I take the magnitude, and this j will also be gone if I take the magnitude. So what do I see? Ideal sin theta 4 pi r into beta. So this is the magnitude of h phi s. So can I write down in this manner? Certainly I can write down in this manner. Right? 1 by 2 into neta h phi s whole square AR cap. And what could be the other answer? That could be 1 by 2 neta mod of E theta s whole square AR cap. So these are two P average expression. And these are the same as what we have studied in our EM wave. In our EM wave, what do we study? E naught square by 2 eta. right? And what do we study? 1 by 2 eta into h naught square. Isn't it the same? They are the same only, right? E naught square by 2 eta h naught square by h naught square into 1 by 2 eta. So this is what we study in our EM wave, and here we got this expression. And always the direction is in the direction of propagation. So here we used to write AP cap or AZ cap because we used to take direction of propagation in the direction of Z. But here we will write AR cap because the radiation is in R direction. So same expression is there. These two you need to keep in mind. So this expression you don't need to keep in mind, but this you need to keep in mind. And also this step should also be clear that if they mention the ES and HS expression, then you should know the process of finding P average. If they have mentioned the phasor form of electric field and the phasor form of magnetic field, then you know the process of finding your P average. Now we have the P average expression. What we need to find? We need to find our P radiated. So now I need to find P radiated. So for that, what is the process? P average dot ds. So till now in EM wave we saw these kind of questions. If you remember, there was a question there. I gave you a rectangular surface and you had the P average expression, and then I asked you to find the total power. Then what did I do? That this was a surface of 100 meter square and it was having a area of dx dy and the direction would be AZ cap. So if I am finding the total power or if I am finding the P radiated, then I need the surface area, no? I need surface area, that what kind of surface area I need to take. Usually it was mentioned in our problems. Previously it was mentioned in our problem that what is the surface area you need to take. ds was always mentioned in your problem. But when you talk about antenna, so antenna is like a point source. Here it is like a point source and it is radiating in radial direction, in the direction of R, right? This is how the antenna is radiating. So always you can assume a imaginary sphere, that let's just say this is my antenna, this is a point source, this is my antenna, and now this is radiating in the radial direction from here, here, in that manner it is radiating. So kind of imaginary sphere can I assume that from this sphere my radiation will be getting out. So by default you need to assume some sphere there. Are you getting this point or not? So in the examination it is not necessary that they will give you any surface. So by default you need to know that if you are talking about antenna, then your ds will be a sphere only. Okay, and it has to be closed surface only because this is a closed surface. Like a sphere is a closed surface, no? So this has to be a closed surface. So here I can put this sign as well. Okay, I will change the color. So here I can put this sign as well. And what about your ds? What do you think? What is your ds? Let's remove it off. So always by default you need to remember this thing, that always by default I will assume a spherical surface, and for spherical surface I just told you which ds we need to take, because what is our P average? Our P average, whatever it is, whatever the magnitude is there, it is in the direction of AR cap. So if I need to take ds, so what that would be? It has to be also in the direction of AR cap. So what that would be, if you remember, dr, rd theta, r sin theta, d phi. So this was in the direction of AR gap. So this we need to drop, and then we need to write down r square sin theta d theta d phi and AR gap. Are you getting this point or not? R square sin theta d phi AR gap. So this is how we write down ds. In the last lecture I told you about this, and if you have studied your coordinate system, then you would already be knowing it, right? That this is how you write down your ds. Now can you find the P radiated? Certainly I can find the P radiated as well. So first you let me know the limits. So what will be the limit of R? R can go from 0 to infinity, right? And sorry, why I am putting the limit of R? Really sorry. I need to put the limit of theta and phi, no? Theta and phi. So what about theta? Limit of theta is 0 to pi. And what about phi? The limit of phi is from 0 to 2 pi. I hope you know this thing. Theta always goes from 0 to pi and phi always goes from 0 to 2 pi. Phi is angle from x axis, so that is 0 to 2 pi, and theta is the angle from z axis, that goes from 0 to pi. Here I need to write down P average expression, so that I will write down. So 1 by 2 eta I naught square dl square beta square sin square although you don't need to remember this answer, whatever that I tell you later on, that you need to remember. This is just for derivation purpose, nothing else. dl square sine square beta square, and here 4 pi square is also there, right? R square is also there, and then yeah, that's it, right? R square is also there. Nita I naught square, there is beta square. Yeah, okay. Now what about ds? Here there is AR cap, no? But AR cap dot AR cap will be done. Here there is AR cap, P average is AR cap, then dot AR cap will be done. AR cap dot AR cap will be 1 only. So forget about that. So now I just need to write R square sine theta d theta d phi. So what do you see? This R square and this R square is getting cancelled, and sine square theta into sine theta, what it will become? Sine cube theta. That's why I was asking you to remember this integration, that from 0 to pi sine cube theta d theta, what that would be? That would be your 4 by 3. If you remember it in the last lecture only, if you go here, some mathematical expression we wrote. Okay, I am not able to find it. Yeah, here 0 to pi sine cube theta, that was 4 by 3. So that I asked you to remember, and it will be used in a lot of problems as well. So that's why I asked you to remember. So when we solve it, what do we get? There is a limit of phi from 0 to 2 pi. There is a limit of phi, but there is no function of phi here. So if I solve the limit of phi, then what I'm gonna get? 2 pi only. Then all this will be constant. All this will be constant. So 1 by 2 eta I naught square dl square beta can be written as 4 pi square divided by lambda square divided by this can be written as 16 pi square. Are you getting this point? And what about neta? What about neta? Neta can be written as 120 pi, right? Neta can be written as, okay, this is not correct. Neta cannot be written as 120 pi. Neta should be written as 120 pi into mu r by epsilon r. 120 pi into mu r by under root epsilon r. This is how it should be written. And if I do sine cube theta d theta, what that would be? 4 by 3. So this is how I am solving the integration. Like somewhere if you need to solve the integration, then you should have the habit of solving the integration like this. Mostly what will happen is that this will never be a function of phi. Very rarely this will be a function of phi. Okay, so all these will come outward. Then if you take the limit of phi, that will be into 2 pi. Now you need to solve the integration with respect to theta. It may happen that you need to solve the integration with respect to phi as well. But mostly what we have seen is that mostly we need to integrate with respect to theta. So when I need to integrate with respect to theta, so or if I need to integrate with respect to phi as well, that also I can do. So that sinusoid and cosinusoid integration I have taught you, and this is how you need to solve it. When you solve it, you can just cancel out certain things. Here you can see the expression of dl by lambda. Here you can see I naught square. Here you can see some pi terms. This and this is getting cancelled as well. So when you solve it, what do you get? That I need to write down. So P radiated. So what do you get? 80 pi square dl by lambda whole square into I naught square by 2 under root mu r by epsilon r. So this is what you get, and this should be in your mind. This should be in your mind. This you need to remember. So what is my P radiated? My P radiated is I naught square by 2 into 80 pi square dl by lambda square under root mu r by epsilon r. And if it is a free space, if they are talking about air, then this factor will be 1. So only this factor will be coming into action. Like what is the power? Power is I RMS square into R, right? So this is the value of R. And what is I RMS square? That is peak value divided by 2, I naught square by 2. If you, what is your I RMS? I RMS is I naught by under root 2, right? And if you take the square of that, what you will get? I naught square by 2. So this is the same thing only. I naught square by 2 into some resistance value. And what is that resistance value? 80 pi square into dl by lambda whole square into mu r by epsilon r, under root mu r by epsilon r. And you know about everything. What is dl? dl is the length. What is lambda? Lambda is the wavelength. Mu r epsilon r, you already know, permittivity and permeability. And I note you already know that whatever the current source that we have applied, peak value of that current source, 2 you already know, 80 pi square you already know. So every single thing you remember. So this is your P radiated. So what we did, this was our antenna, and we gave it some supply. I naught cos omega t. Now this antenna is radiating some power in the radial direction. Since this is P radiated, this power is not a vector quantity, but time average pointing vector is a vector quantity. P average is a vector quantity, right? But what is the total power that is radiated? That is not a vector quantity. So P radiated is not a vector quantity. So how much power it is radiating? This much power it is radiating. So this you need to keep in mind. Also, this is not a function of R. P radiated is not a function of R. Just it is depending on the length and certainly on the source as well, whatever the source you apply, and also on the length, that what is the length of your dipole antenna. This is your Hertzian dipole. So what is the length of your Hertzian dipole antenna? It depends on only two factors, right? The source and the length, and certainly medium as well, mu r by epsilon r as well. But if it is a free space or if it is a air, then you don't care about this expression. So medium, dl and I naught. Source, length and the medium. It depends on only three factors. It doesn't depend on the R value. Okay. So what is R? R was the point where we found it out. Like R was the point where we are finding all the expression. If you see from here, R was the point. So R was the radial distance from the dipole antenna where we found out the expression of H phi and E theta. But when we find out the value of P radiated, we got to know that it is not a function of R. So this is our P radiated. Now, if antenna is radiating some power, that means this power should be coming from this source only, no? Like if this guy is radiating some power, that means this is coming from this source. Or if you remember simple network circuit, if you say that I square R is the power that is radiated across this resistor, or you can say that is dissipated across this resistor. I naught square R is the power that is dissipated across this resistor. That means that power should be coming from this battery, right? If there is a resistor and that is dissipating I naught square power, that means that power would be coming from the battery, no? So here also, if your antenna is radiating some power, that means that would be coming from the battery. So can you replace antenna as a resistance? If I replace antenna as a resistance, then what I would get to know that how much power is dissipated in that resistor. What I mean to say is that, let's see it on the next slide. So now this is my antenna. Now if I replace this antenna, this is the part of transmission line, I am not doing anything with that. And if I replace this with a resistor, R radiated, and this is my source, that is I naught cos omega t. Now I am assuming that in the transmission line there is no loss of the power. What I am assuming? That there is no loss of the power in the transmission line, that whatever the power that is here, the same power is reaching here. This is what I am assuming, that this transmission line is lossless. There is no loss of the power. Also, I am assuming that complete power is transferred here. That means there are no reflections. As of now, this is what I am considering. But certainly we will discuss about it more. We will discuss about this transmission line, that this transmission line can result in some losses as well. So certainly we are going to discuss about it, but in the third or fourth lecture. Probably in the fourth lecture, or certainly in the fifth lecture, okay? In the fifth lecture, we are going to discuss about this thing. But as of now, what I am assuming is that there is a current source and our antenna was radiating this much power. So now I have replaced antenna with R radiated. So now what I can do is that I will find the power that is dissipated in this resistor. So what is the power that is dissipated in R radiated resistor? What I am saying, power dissipated in this resistor. Power dissipated in resistor R radiated is equals to the power radiated by antenna. Say yes or no? So what do you think, what is the power dissipated in the resistor? That is I naught square by 2 into R radiated, or you can write down, if you get confused, that would be I RMS square into R radiated, or you can write down I naught square by 2 into R radiated, or you can write down this is equivalent to this guy, that is I naught square by 2 into 80 pi square dl by lambda whole square under root mu r by epsilon r. So what you are getting here, your R radiated is 80 pi square dl by lambda whole square under root mu r by epsilon r. So needlessly I put that in box. Box is not necessary here. Here the box is necessary. So what I prefer is that I prefer remembering R radiated formula. I don't remember P radiated. I remember R radiated. And if I remember R radiated, can you tell me P radiated? Yes. That's why from the source I naught square by 2, I need to take RMS value. So I naught square by 2 into R radiated. What is my R radiated? This is my R radiated 80 pi square dl by lambda whole square under root mu r by epsilon. So better remember R radiated. Certainly we are going to write down in one page only that what all you need to remember. But as of now, what do you see? This expression you need to remember. If you remember h phi x expression, then certainly you remember E theta expression. Just you need to multiply by neta, right? And then this thing also you know that AR is equals to A theta cross A phi, and direction also you need to remember that for H we have phi component and for E we have theta component. And also what else you need to remember? This you need to remember that what is my AS expression, okay? And in AS expression mu was also there. This also keep in mind, okay? We will certainly write down all these things in one page only. Then this is your P average expression. These things you can remember, and this is your P radiated and R radiated you got. So better remember R radiated. From R radiated you can write down P radiated very easily. So for Hertzian dipole, if we write down all the summary, so what we assumed that our antenna is placed along z axis. This has been the assumption. Now if antenna is placed along the z axis, then I need to find the power radiated at point P. So for that, first I wrote down ES, then HYS I got, then E theta S I got, then R radiated and P radiated. So these expression I need to keep in mind. So what was your AS? That was mu I naught dl upon 4 pi r e to the power minus j beta r Az cap. This was your AS. Will you able to keep this thing in your mind? Mu I upon 4 pi r, then certainly here if I write down dl vector, then it would be Az gap. Okay, this is how you can write down. Basically why Az gap? Because my current is flowing in the direction of z. My antenna is placed along the direction of z, that's why I am writing Az gap here. So this thing will you be able to keep in mind? Certainly. And if I need to replace Az gap, then how I will replace it? Because what do I remember? That Az gap is equals to z is equals to r cos theta. Z is equals to r cos theta. So from here I can write down AR cap cos theta, then differentiation of this sin theta, sin theta A phi cap. So this is my Az gap. So this also I can keep in mind. This was the first expression that I need to keep in mind. Then what about H phi s? So that is ideal sin theta upon 4 pi r. I say ideal, but I will write down I naught. Why do I say ideal? Because it is easy to remember, no? Ideal. So that's why I say ideal. So I naught dl sin theta upon 4 pi r j beta e to the power minus j beta r, and certainly the component is in phi direction. What about E theta s? So simply neta, and then not just the magnitude. Actually I should not write magnitude like that, because if I take the magnitude, then this j term will not come, no? So let's write down the complete expression only. So E theta s is I naught dl sin theta, just neta will be multiplied, nothing else, and certainly direction will also be changed e to the power minus j beta r A theta gap. Also we can see is that the direction of radiation is equals to the cross product of direction of electric field and the direction of magnetic field. This also we can see here. And what about the R radiated we got? So this formula we need to keep in mind, 80 pi square into dl by lambda whole square into mu r by epsilon r under root mu r by epsilon r. Okay. This we need to keep in mind. And what about P radiated? P radiated is I naught square by 2 into R radiated. So when you revise it, this slide only you need to revise. That's it. No derivation, nothing else. What we need to remember? The magnetic vector potential. How will I remember? Only thing is here mu will come. And how you can keep in mind that I have already told you that del cross A is equals to mu H. So mu will come. Okay. So that is mu I naught dl 4 pi r. There is no sin theta, nothing else. Sin theta will also not come, and mu will also sin theta will not come here. Here extra term is mu upon 4 pi r e to the power minus j beta r, and the direction will be in the same direction as current, and current will always be in the direction where your antenna is placed. So antenna is placed along z axis. So current will be AZ gap. And if I need to write it down in terms of my AR cap and A phi cap, then also I can write down. I can replace my AZ gap, right? And then I need to remember my H phi s component, that is ideal sin theta upon 4 pi r, ideal sin theta upon 4 pi r into j beta e to the power minus j beta r A phi cap. What about E theta s? Multiplied by neta, rest all the things are same. Then R radiated I will keep in mind. And certainly I need to remember my P average as well. But what else I need to, what all things I need to remember in P average? So if I write down my P average, so in P average I just need to remember these things, that it is equals to 1 by 2 real of ES cross HS conjugate, or it is equals to 1 by 2 neta mode of E theta s square, direction is in direction of radius, or it is equals to 1 by 2 eta mode of H phi s whole square, direction is in the direction of radiation. So if you just remember this slide, your job is done about Hertzian dipole. You will be able to solve all the problems of Hertzian dipole antenna just by remembering this slide. A lot of students don't prefer remembering this formula, but certainly if question is coming on Hertzian dipole, these questions will be coming on this formula. Only people remember these two things, and there also they forget this term. That is the worst mistake you can do. If they don't give the medium as free space, like usually people write down that R radiated is this. No, this is not correct. This is correct only for the free space. But if the medium is something else, then this will also come into action. Okay, so always remember R radiated correct formula. If you remember R radiated, then your P radiated is a kickback for you. And if you remember H phi s, then E theta s is a kickback for you. And P average we can copy as it is, ditto from our EM wave propagation. In the second chapter we studied about this thing, so ditto same thing I need to copy here, right? And conversion I can do, and this I already know. So that's it about our Hertzian dipole. Again, some things are left. What is that? That is the radiation pattern. So now we are going to see radiation pattern. So what do we do here in the radiation pattern? So you let me know one thing. When we studied wave polarization, right? In AM wave we have already studied this chapter, no? Wave polarization. So in our wave there is E field as well, there is H field as well. Both fields are there. But when we studied wave polarization, we only talked about E field, right? We were seeing the orientation of E field, that if there is a AX cap, AY cap, what is the phase between these two, and if phase is pi by 2, then it will be circular. If phase is a multiple of pi, then it will be linear, and if something else is there, then it will be elliptical. So we were talking about only E, right? Certainly there was H also present, but we were only talking about E. So here also we need to see how our radiation pattern will look like. What we need to see, that how our radiation will look like. But here we will only see about E. We will not talk about H. Is there any reason behind that? No. There is no specific reason. There is no specific reason behind that. You only talk about E. In wave polarization, is there any specific reason that I only talk about E? No. But this is how it is defined. So radiation pattern is also defined with respect to E only. Same as wave polarization. So what we need to study? We need to study about electric field. And what we are going to find? We are going to find the normalized value of E field. And what do you mean by normalized value of E field? So normalized value of E field is whatever the E theta x expression you are getting divided by the maximum value of E theta s. And I don't know why did I put this as mode. There is nothing like mode here. It is just the normalized value of electric field, which will be a function of theta or phi. Normalized value of electric field which will be a function of theta or phi. So that will be E theta s. I should not write E theta s because always it is not necessary that your electric field will be in the direction of theta, right? It is not necessary that always the electric field will be in the direction of theta. Here electric field is dancing in the direction of theta in our case, but it is not necessary. So what I am writing here, I should write Es divided by E max. Es divided by Es max. Okay, so this is known as normalized value of E field. So when we draw the radiation pattern, what do? We take the normalized value of electric field and we draw it with respect to theta and we draw it with respect to phi. Here we keep phi as constant and here we keep theta as constant. You will see it, okay? You will see it that what we are going to do. So as of now, you just find out the normalized value of E field. What will be the normalized value of E field? So here what we are having? We are having electric field component in the direction of theta only. And what will be the maximum value? That I need to write down. So this is my electric field component, that is neta ideal sin theta upon 4 pi r j beta e to the power minus j beta r divided by a into a theta gap. Now divided by the maximum value. If I need to find the maximum value, that means sin theta will be 1. If I need to find the maximum value of this complete expression, then I know dl 4 pi r neta, all these are defined. Beta will be coming from the resource. R will be given in the question that at which distance I need to find. dl will be also given by the user only, that what is the length of your Hertzian dipole. I naught will be also given by the source only. So this will come from source, this will also come from source. All these are there. But if I need to maximize this value, then what I can do is that I can take theta as 90 degree. So what will be the maximum value? Sin theta, what is the maximum value of sin theta? That is 1 only, no? So what do we get? Neta ideal 4 pi r into j beta e to the power minus j beta r e theta gap. So what did you get? Your normalized value of electric field is coming out to be sin theta. That's it. Always it will be the function of theta or phi. So in the expression, if you get any function of theta or phi, so just pick that up. Here, if I see this expression, then which, if I see, no, not this one, sorry. If I see the expression of E, then which expression is the, which function is the, sorry, what I should say, which quantity I can tell, or which function only I can say. So which function is the function of theta and phi? So this is the function of theta and phi. So here sin theta is the function of theta and phi. So my normalized value of electric field is coming out to be sin theta. So now I need to plot sin theta versus theta and sin theta versus phi. And how will I plot it? That I am gonna show now. Okay, so this value I need to plot. So always whenever they ask the radiation pattern, what you need to pick? You need to do the exact expression divided by the maximum value. And the maximum value you already know, right? Okay. Yeah. So this is what we need to plot now. Now there will be two planes. In two planes we are going to plot it. Although this will be a 3D plot, right? Radiation will be in the 3D. If this is my Hertzian dipole, then it will radiate in 3D, no? Like it will not radiate in 2D. From here also, radially it will radiate everywhere. So plot will be 3D. But we will draw two plots in 2D and then we will combine it. Are you getting this point? What we are going to plot? We are going to plot two plots in 2D and then we are going to combine it and then we will see the 3D plot. So this is what we mean by radiation pattern. So what we are going to do? We are going to plot this versus theta and this versus phi. When I am plotting with respect to theta, that means I will put phi equals to 90 degree, and when I am plotting with respect to phi, at that time I will put theta equals to 90 degree. So what do you think? What is theta equals to 90 degree? Theta equals to 90 degree. That is your xy plane. Say yes or no? Theta equals to 90 degree is your xy plane. No, from z axis you need to go 90 degree. So that is your xy plane only. No. So theta equals to 90 degree is your xy plane. What about phi equals to 90 degree? What is your phi equals to 90 degree? Phi equals to 90 degree. What is your phi equals to 90 degree? From x axis I need to go 90 degree angle. That means I am reaching on zy plane. Phi equals to 90 degree my zy plane. Do you agree to this point or not? Right? So this zy plane is known as E plane and this is known as H plane. It should be there in your mind. Does this H plane has anything to do with the magnetic field? No. Here we are going to plot electric field only, normalized value of electric field only. But we will plot it on E plane and H plane. So don't think that on H plane I will plot H value and on E plane I will draw E value. Nah. On both E plane and H plane we are going to plot normalized value of electric field only, not magnetic field. What we are going to plot? Electric field only. On E plane as well, on H plane as well. On this plane I will draw and on this plane I will draw. On which plane? On this plane and on this plane. So your this plane is known as H plane and this plane is known as E plane. How you can remember? So this is just a way to remember. This is not the reason why it is known as H plane. This is not the reason why it is known as H plane. This is just a way to remember. How will you remember? H stands for horizontal. Horizontal. H is horizontal. And E can stand for elevated. Elevation. From E you can think about of elevation. So if there is something elevation, that means that is this plane. And if I talk about horizontal, then this is this plane. This is just a way to remember. Like you already remember this is X, this is Y, this is Z. So when I say H plane, so you will think horizontal. Okay, that means XY plane. And when I say E plane, yeah, so what I was saying, when I say H plane, you need to think of XY plane. And when I say E plane, you need to think YZ plane. So how will you remember it? H stands for horizontal, E stands for elevation. This is not the actual meaning of this. Actual meaning is E stands for electric only, H stands for magnetic. This is just a way to remember. What is the way to remember? H horizontal, that means XY plane. E elevated, that means this YZ plane. This is just a way to remember. Okay, this is not the actual reason. Let me tell you the actual reason, but no one will ask you why it is known as E plane. So let's just say in YZ plane I take any point. I take any point, this point is some Q point. On YZ plane I am taking this point. Now on YZ plane, what will be my AR cap? At this point, what will be my AR cap? So you need to join this point from the origin. So this will be your AR cap. And what will be my A theta cap? This will be my A theta cap, right? Because in the direction of theta, this will be my A theta cap. So on YZ plane, what you are getting? You are getting the radial direction, or you can say you are getting the direction of radiation, and you are getting the direction of electric field, because your electric field is in theta direction, right? And your radiation is in R direction. So on on YZ plane, you are getting the direction of electric field and you are getting the direction of radiation. Where will be your magnetic field? Your magnetic field is in phi direction, right? Your magnetic field is in phi direction. That means that will be going inward, because on this plane phi is equals to 90 degree. So what will be your phi? Phi will be going inside. Phi will be going into the screen. So that will be your A phi. So no component of A phi is on YZ plane. No component of A phi is on YZ plane. That means no component of magnetic field is there on YZ plane. So on YZ plane, you only get the direction of radiation and direction of electric field. Are you getting this point? So that's why what is the reason? That's why we call it E plane, because on the YZ plane you only get the direction of electric field and the direction of radiation. Same goes for H plane as well. So on H plane, what do you get? On H plane, if I take any point here, so what will be my AR cap? This will be my AR cap. And what about my A phi cap? This will be my A phi cap. Where will be my A theta cap? So from upward direction theta is coming, so my A theta cap will be going into the plane. So on XY plane, if I talk about on XY plane, so on XY plane you are getting the direction of radiation, you are getting the direction of radiation, and you are getting the direction of a magnetic field. So this is the reason, that's why it is known as H plane and E plane. No one will ask you this, neither in interview, nowhere it will be asked, but this is just a reason that I wanted to tell. So what is the reason? That on H plane, on XY plane, when you take any point there, so you see there that you get the AR cap and you get A phi cap. So that means you are getting only the component of H field and the radiation direction. And when you talk about YZ plane, so on YZ plane if you take any point, so there you can get your A theta cap and AR cap. A theta cap and AR cap you can get there, right? So on YZ plane, I am only getting the direction of electric field and the direction of radiation. So that's why that is known as E plane. No one will ask you, just a way to remember, I have told you horizontal plane and elevation plane. This is not the actual meaning, but this is just a way to remember, right? So now the path is clear. Now what we need to do in this process, what we need to do, we need to plot the normalized value of electric field with respect to theta versus theta. We need to plot when we fix phi value, and we are fixing phi value as 90 degree, and then we need to plot our normalized value of electric field with respect to phi when we fix the theta value, that is theta equals to 90 degree. So this is what we need to do in this particular process. All good? Okay, yeah. So now let's define some parameters. So this is my normalized value of, what is this? This is my normalized value of electric field. So with respect to that, I am defining position of nulls, position of half power, and maximum radiation direction. Maximum radiation direction I could have write it down. So what do you mean by position of null? So position of null means at what value of theta your normalized value is becoming 0. Position of null means your normalized value of electric field should be 0. At what values of theta? And what is the range of theta? Theta can be from 0 to 180 degree only. From 0 to pi you can say. Say yes or no? Theta can be from 0 to pi only. Because theta is the azimuthal angle, which can be from 0 to pi only. So range of theta could be from 0 to pi. So sin theta is equals to 0. So theta you are getting as 0 degree or 180 degree. Now no one will say that, sir, other values can also come. No, 0, 180, 360 also it can come. 360 is equals to 0 degree only, no? And we will not write any value apart from pi. Okay. So theta and 180 degree. What about position of half power? So the power that is half of the maximum value. At what value of theta your power is half of the maximum value? What value of theta where power is half of the maximum value? So when I find out the half power, what do you think what I should equate it to? When I am finding half power, so my normalized value of E field should be equated to what? It should be equated to 1 by 2 or it should be equated to 1 by under root 2. Think about it. When I am finding the half power, I am finding the position of half power. That means I am finding the value of theta where your power is half. So will I equate it to half or 1 by root 2? Half of what? Half of the maximum value. What is the maximum value of sin theta? That is 1. But here we did not find the maximum value of sin theta. Why is that so? Because what is your P average? P average is proportional to normalized value of electric field square. Say yes or no? So your power radiated should be proportional to sin square theta. So if I am talking about half power, that means normalized value of electric field I should keep it equals to 1 by under root 2, no? Because maximum value of a normalized electric field is 1. And at 1 by root 2, my power will be half of that. Because 1 by root 2 whole square is half only. Here the maximum value of sin theta is 1. And if I need to take half value, that means sin square theta should be equals to 1 by 2. That means sin theta should be equals to 1 by under root 2. So electric field, normalized value of electric field should be kept as 1 by root 2. If I need to find the half power position, what I need to find? Position of half power. So that should be 1 by root 2. So sin theta should be equals to 1 by under root 2. So from here, theta is equals to 45 degree and 135 degree. And where will be the maximum radiation? So at what value of theta you will get the maximum radiation? That means at what value of theta you will get the maximum value of a normalized electric field. So what is the maximum value? Sin theta should be equals to 1, or you can write down my En should be equals to 1, or sin theta should be equals to 1. So theta should be equals to, where it would be 1? It would be 1 at 90 degree. Now no one will say that, sir, it would be 1 at 90 plus 2 pi. So that also you can write down. No, only one angle I will write down till 90 degree, because I need to take in the range of 0 to pi. Are you getting this point? So position of null, these kind of questions they can ask in the examination, that what will be the position of null, what will be the position of half power, and what will be the maximum radiation. Now let's plot the radiation pattern. So what we are plotting, radiation pattern we are plotting. So one in E plane I need to plot. What is my E plane? E plane elevation you need to think YZ. Are yaar, this is E plane is YZ plane, right? Not X. E plane is YZ plane, right? E plane is YZ plane, no? This is your E plane, and your H plane is XY plane. Your H plane is XY plane, but this is YZ plane. Okay, here phi is 90 degree. So what will be your normalized value of electric field here? You need to put phi equals to 90 degree. This is the normalized value of electric field. Can you put phi equals to 90 degree here? No, there is no function of phi, right? And at z axis there is no function of phi. So now I need to plot En versus theta. So versus theta I need to plot. What is the value of theta here? 0 degree. What is the value of theta here? 90 degree. What is the value of theta here? Can you tell me? Minus 90. No, plus 90. What did I tell you? When you define theta, then from up to down, angle is defined from up to down. So here as well, or here, or here, or here, the theta will be same. If I talk about this angle now, let me take these two pen, and if I talk about this angle, that what will be this angle? What will be this angle? This angle will be, let's just say, some 120 degree angle. If this is 120 degree angle, and now if I rotate it, in this manner, and now if I ask you what is this angle, this is also 120 degree only. So if I completely rotate this vector, like at one point only, if I completely rotate it, so everywhere the angle will be 120, 120, 120. So here also it is 90 degree. Here also it is 90 degree, and this is also 90 degree, right? This is how we define the theta value. You need to study coordinate system. You need to study spherical coordinate system. Then only you will be able to understand these points. So this is 90. This is also 90. And what about this? This is your 180 degree. Somewhere in between you will be getting 45 degree. So that we are not caring about. So now with respect to theta I need to plot. So at 0 degree what you are getting? 0 value. At 90 degree what you are getting? Value 1. At 180 degree you are again getting 0. At 90 degree you are getting value 1. Let's talk about at theta equals to 45. At theta equals to 45. So at theta equals to 45 what you are getting? Some 1 by under root 2. Let's just say this is some 1 by under root 2 value. If this is 0, this is 1, this is some 1 by under root 2 value. What about this? What is this angle? This angle is theta equals to 135 degree. So at 135 degree what you are getting? Some 1 by under root 2, let's just say. What do you think what will be this angle? So from here I need to measure. From where I need to measure? From here I need to measure. So let's wait. This angle will also be theta equals to 135 degree. So at 1 by 35 degree, let's just say this is some value, that is 1 by under root 2. And what about this one? This is also some. This angle is also 45 degree. This angle is also theta equals to 45 degree, and magnitude here is also 1 by under root 2. So now if I make it, it will be somewhat like this. अच्छा नहीं बन रहा यार. And here also it will be somewhat like this. But let me make it with circle. It will not be a circle. Are you getting this point? How it will be a circle? No, it is sinusoid, right? At 0 you are getting 0 degree. At 45 degree you are getting 1 by under root 2. At 90 you are getting 1. So it can never be a circle. Certainly it will never be a circle. Because if I talk about circle, this will not be a circle, but here just to show it I am making as a circle. Okay, don't think this is a circle, but just to show it I am making this as a circle. And here as well I am making the same circle. Both will be symmetric. Always the geometry will be, whatever the radiation pattern you draw, always it will be symmetric about z axis. Why is that so? Because whatever the angle you get here, whatever the angles you get here, whatever the angles you get on this side, the same angle you get on this side only, no? So it will always be a mirror image. It will always be a mirror image about z axis. Because this is theta equals to 0, 90, and this is 180. This is 45, this is 135. What about this? This is 45, 90, 135, 180. So this is how we will get. Certainly it is not a circle. It is not a perfect circle. The radiation pattern is not a perfect circle. Okay. So always keep this in mind. Just to show it in a good manner, I have made it a circle. But don't think that it is a circle. Okay. So this magnitude is 1 by under root 2. This is your 1. This is also 1 by under root 2. This is also 1 by under root 2. And this magnitude is 1. So this is how my radiation pattern in E plane will look like. In E plane, what do we do? In E plane, we put phi equals to 90 degree. And when I talk about phi equals to 90 degree, that means I am talking about YZ plane. Now I need to think about theta value. So theta value always is measured from Z axis. So at Z axis, theta is 0 degree, then 45, 90, 135, 180. Similar is measured on this direction as well. This is how we define the value of theta from 0 to pi. So here as well from 0 to pi. And this is the radiation pattern we will get. When I put theta equals to 0, you are getting 0. When I put theta equals to when I put theta equals to 45 degree, 1 by under root 2, this is 1, then again 1 by under root 2, then again 0. Same pattern you will get this side as well. Okay. Now what we need to plot? We need to plot at H plane. So for H plane, I need to put theta equals to 90 degree. Here I put phi equals to 90 degree, but here I need to put theta equals to 90 degree. So my normalized value of n sin 90, what that would be? 1 versus what I will plot. If I have fixed theta, that means versus phi I will plot. In which plane? In H plane. So no matter whatever the value of phi is there, what is the value of phi here? Phi equals to 0 degree. What is the value of phi here? Phi equals to 90 degree. What is the value of phi here? Is it 0 degree? No, because phi is the angle that is measured from x axis. So 0, 90 degree, this would be 180 and this would be 270, right? Angle is measured from x axis towards y. So from x towards y, 90, 180, 270 and 0 degree. No matter whatever the value you put, always normalized impedance value is 1. So at 0 degree also it is 1. At here also it is 1. 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 Always it is 1, 1, 1, 1, 1, 1, 1, 1, 1. That means it will be a perfect circle. Because normalized value of electric field here is always 1. Are you getting this point or not? When I draw the radiation pattern in H plane, I got to know that my normalized value of electric field here, my normalized value of electric field is always 1. So I need to plot 1 versus phi. What I need to plot? I need to plot 1 versus phi. So if I change the value of phi, always I will get magnitude as 1. So on xy plane you will get a perfect circle. This is a perfect circle. Certainly this is a perfect circle. So no matter if your phi is 45 degree, if it is 135 degree, if it is 180 degree, if it is 95 degree, if it is 35 degree, if it is 180 degree, always you are getting the value to be 90, 180, 135. 225 आएगा यहाँ पे, yes, 225 degree, and here what will come? 315 degree. So always your value is 1 only. So this is in my xy plane and this is in my yz plane. Can you combine both of them? One is in xy plane and one is in yz plane. Let's make the 3D pattern now. So this is how the 3D pattern will look like. Or shall I draw it again? And yeah, one more thing. Where was your antenna placed? Where was your antenna placed? Your antenna was placed along z direction. Your antenna was placed along z direction. And here where will be your antenna? X cross y z. That means coming towards you. So here x cross y is z and antenna is placed along z axis. So here my antenna is placed. This is my antenna. This is my antenna. And here where is antenna? This is your antenna. So position of antenna is also necessary. Antenna is placed like this, then here there is a radiation pattern, here there is a radiation pattern, and there is a radiation pattern downward. So if I make it on, let's make it again because it is important for you. Let's make it again. So this is your z axis, this is your y axis, and this is your x axis. I am making minus x as well. This will be minus x, this will be minus z, and this will be your minus y. For a better visualization, I will give you a lot of visualization as well. Don't worry about that. Z, x, and y. What this is? Minus x, minus y, and minus z. So what do you see? In xy plane there is a circle. This is my xy plane, no? So in xy plane there is a circle. So that circle I need to show something like this, no? The circle should be shown something like this. Say yes or no. It is in xy plane. The circle is in xy plane. Are you able to imagine this? Now here you are having two circle kind of things. Two circle kind of things on yz plane. On yz plane. What is the yz plane? This is your yz plane. So here you are having two kind of circle kind of thing. Just make sure one thing, that this is the magnitude 1 and this is the magnitude 1. And here as well on yz plane you are cutting at magnitude 1, you are cutting at magnitude 1. On y axis you are cutting at magnitude 1, you are cutting at magnitude 1. So two circle kind of things are there. Certainly they are not perfect circle, but this is how we need to show it. Certainly they are not perfect circle, but if I show it, this is the way I can show it, right? Right? So this is my pattern in E plane and this is my pattern in H plane, making sure that my antenna was placed here. This is how my antenna was placed. This is my antenna. अरे यार सही से नहीं बना. This is my antenna. So these patterns can be asked. Now you tell me one thing. This pattern we drew for phi equals to 90 degree and this pattern we drew for theta equals to 90 degree. We fixed some value, no, that theta equals to 90 degree, then I got this pattern. Now theta can be from 0 to 180 anything, no. I only drew for 90 degree. I made this pattern only for 90 degree. I am only talking about what I am talking about. Now I am talking about this is z, this is y, this is x. So I am talking about now this pattern which is in H plane, which is a circle. So that I draw for theta equals to 90 degree. But theta can be 45 degree as well. For theta equals to 45 degree, what you will get? For theta equals to 45 degree, if you get what will be the normalized value of theta equals to, normalized value of theta equals to 45 degree? That would be sine 45, that would be 1 by 2, 1 by under root 2. And where will be theta equals to 45 degree? That would be somewhere here in the air. Let's just say this is my x, this is my y. Sorry, this is my z, this is my y. This is my z, this is my y. So theta equals to 45 degree will be somewhere here. And then I need to make a circle of 1 by under root 2. If I am plotting it with respect to phi, that means there will be a circle of 1 by under root 2 radius. That means that circle will be somewhat like this. Then for theta equals to 30 degree, that circle would be somewhat like this. Then theta equals to 0 degree, that circle will be 0. Basically, if there is one circle for theta equals to 90 degree, then there will be another circle for theta equals to 45, then another for theta equals to 30 degree, then for 0 it will be 0. Somewhere here as well there will be some circles, and somewhere here as well there will be some circles. So it is like circle, 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 and then downward as well the same thing. Circle, 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 circle. Like 0 radius circle, then circle are getting bigger, then at 90 degree you are getting the biggest circle, and then circles are getting smaller. Are you able to visualize the structure? Let's just say this is some z, this is y, this is x. Let's give you more visualization. This is your z, this is your y, and this is your x. So there is a circle. So circle will be like a conical way. In a conical way, there will be circles. Like here also there will be a circle. There is a circle. There is a circle. There is a circle. So there will be circle, circle, circle like this. Are you getting this point? So when I am plotting with respect to phi, so theta value I can put anything. Here I put theta equals to 90 degree. That was a specific case. But if I am plotting with respect to phi, that means any value of theta I can put, no? 45, 30. So one case I have drawn here. But if I needed to plot other cases, then those cases would go like this, like in a radial way. like from here to here, in a radial way, there will be circles. In a radial way, there would be circles like this. You are able to visualize it, say yes or no. There will be circles like this. And certainly downward as well. Certainly downward as well, there will be the same kind of things, no? Like this thing you made upward. This thing you made upward, but downward as well, there will be same kind of thing. There will be circle, circle, circle in this manner. In this manner, there will be circle, circle, circle. Are you getting this point? Certainly, I will show you how the equivalent circuit would look like, how equivalent radiation pattern will look like. But are you visualize this thing? So this we talked about with respect to phi. Now, if I plot with respect to theta, what I am going to plot? Normalized value of E, which is equals to sine theta. Now I need to plot with respect to theta. Okay. So here what did I put? Here I put phi equals to 90 degree. But phi could be anything, no? Phi could be 0 degree as well. If phi is 0 degree, that means I will get these two kind of circles. These two kind of circles. They are not perfectly circle. These two kind of circle on ZX plane. Say yes or no? What I mean to say is that this is my Z, this is my X, and this is my Y. Now I am saying that this I have drawn for phi equals to 90 degree. But if I take phi equals to 0 degree, where will be phi equals to 0 degree? On X axis. So if I take phi equals to 0 degree, if I take phi equals to 0 degree, then I need to plot En sin theta versus theta, sin theta versus theta. So at Z axis, what is the value of theta? 0 degree. At Z axis, the value of theta is 0 degree. What is the value of theta at X axis? 90 degree. And what is the value of theta here? That is 180 degree. And similarly, what is the value of theta here? That is 90 degree, and downward it is 180 degree. So how it will go? Some circles here, circles here. In between as well, if I talk about somewhere 45, if I talk about phi equals to 45 degree, so here as well there will be circles. If I talk about phi equals to 135 degree, so here as well there will be circles. So these two circles will be keep on moving. If I show you like this, these are the circles, then they will keep on moving around Z axis. In the whole manner it will move. In the whole circular manner, these two circles will move. They are not perfectly circle, again I am saying it, but these two circles around Z axis will keep on moving with respect to phi. This we have drawn for a specific value of phi. So what is happening here? That these two circles are moving in this manner. These two circles around Z axis, they are moving in this manner. And what about this circle? This circle is getting up and down with less radius. Are you able to think it? That how the radiation pattern is actually looking like. So this is how the actual radiation pattern will look like. Now you are able to see it in 3D. That these two Enoch, I should not say Enoch, or you can say these two kind of circles only, they are moving constantly. And this circle that is downward, that is going up, but radius is getting close. So here what you can see is that here radius is 0. So the same kind of structure will be downward as well. So this is how the radiation pattern will look like. No one will ask you in the examination, but it is something that will make you feel good about Hertzian dipole. You are able to see the radiation pattern of Hertzian dipole. Say yes or no. Is it good visualization or not? So radiation pattern is a very important topic. I should not say important topic, but a very good topic. And we can expect question from here as well. So radiation pattern is a very good topic, and usually students are confused about it. But we have studied it. How did we start? First we saw this, that what we need to do. We need to plot only the sin theta term I will pick, or you can define E theta divided by E theta max, that is sin theta. Then with respect to theta and with respect to phi. When I plot with respect to theta, that means phi equals to 90 degree, and when I plot with respect to phi, that means theta equals to 90 degree, right? Then I started plotting it, that how it will look like. But before that I defined some values. This is the position of null, this is the position of half power, and this is the maximum radiation. Okay, so this also we can keep here. Somewhere I can keep it. And here I should not write P radiated. That wouldn't be correct. Yeah, that would be fine. And then we found these values and we plotted it. The plot you must have understood. Antenna, then theta value I am changing, and here also I will get the same thing, and then on xy plane I will get the same thing. But what I am plotting then normalized value of E. Then I combine both of them. When I combine both of them, so I combined it, that is very easy to visualize. But the thing is, all these we have drawn for a specific value of theta. But if I take all the values of theta, then how this circle will look like? And if I take all the values of phi, then how these two circles will look like? So these two circles will move, and this is how the circle of theta equals to 90 degree will move. This circle will move in upward direction, and these two circles will move like this. And when you combine both of them, this is how the pattern would look like. Is this good visualization? Do you know? Is it a good visualization or not? Right? So this is how the radiation pattern looks like. Okay. So I hope you must have understood this in a very good manner. क्या हो गया यार? Yeah. Okay. So no one will ask you, but like they can ask you to draw the radiation pattern for specific plane only. They will ask you to draw the radiation pattern on E plane or in H plane, and 99% chances are there that they will ask you the radiation pattern of E plane only. Okay. No one will ask you for H plane, because in H plane we put the value of theta equals to 90 degree. That means this is 1 only. So this is a constant value. So it will be a perfect circle. But usually they ask about this. Okay. Now a few more terms are defined. What all are those terms? So okay, let me add a page. I will add a page afterward, and there I will copy this. So a few terms are defined. 45 degree, 90 degree. So terms are half power bandwidth. Half power bandwidth. As of after this, I will always write half power BW, half power bandwidth. What is that? The angular distance between half power point. So half power point is 45 degree and 135 degree. So half power bandwidth is 135 degree minus 45 degree. That is 90 degree. You can call this as half power bandwidth as well. 135, 45. That is also 90 degree. Here also it is 90 degree. Second is first null bandwidth. First null bandwidth. I will write it down. First null bandwidth. So what that is? The angular distance between the nulls. Angular distance between the nulls. So null you are getting at 180 degree and at 0 degree. So what is your first null bandwidth? That is 180 degree. The angular distance between the nulls. Now why this is first word is there? You could have called it null bandwidth, no? Because we know that the location of nulls are 0 and 180 degree. Location of nulls are 0 and 180 degree, and if I need to find the position of nulls, that means 180 degree it would be. The position of nulls will be 180 degree. Sorry, position of nulls. What I am saying, position of nulls is 0 degree and 180 degree. And if I need to find the bandwidth, then it would be 180 degree minus 0. So why you are calling it first null bandwidth? Why you cannot call it null bandwidth only? So when we see the radiation pattern of other antenna, this is only Hertzian dipole antenna we are going to see. So when we see the radiation pattern of other antenna, we will see that there will be a lot of lobes. Here there is only one lobe, no? Like this lobe is there. This is my antenna, and here there is one lobe only. Right? But when we see other kind of antenna, when we take other length, so there will be a lot of lobe. So the lobe having maximum radiation. Where is the maximum radiation? This is the maximum radiation. Here there is only one lobe. So this lobe only having the maximum radiation, no? But when we define first null bandwidth for these kind of antenna, so what we will see, the lobe having maximum radiation, and for these maximum radiation, what are the null point? So with respect to that, we will define our first null bandwidth. So when we study about these antennas, like it would be 3 lambda by 2 length antenna. This would be 3 lambda by 2 length antenna. So there I will tell you that why this first word was there. Okay. As of now, null bandwidth or first null bandwidth both are the same thing for Hertzian dipole, because here there is only one lobe. There is only one lobe. But if there were multiple lobe, then you had to define the first null bandwidth for the maximum radiation lobe. Now the maximum radiation lobe could be this as well, it could be this as well, it could be this as well, it could be anything. So as of now we are defining it for one lobe only, which is this one. So that is the maximum radiation lobe only. Okay. So this you got. And what could be the other point? The other point could be where you are getting the maximum radiation. Maximum radiation means maximum value of maximum radiation. If I ask you maximum radiation, that means I'm asking you the maximum value of your normalized value of electric field, and that you are getting at theta equals to 90 degree. Here we find out maximum radiation that is in the direction of theta equals to 90 degree. So can you say my maximum radiation is perpendicular to the antenna, because this is my antenna and my maximum radiation is in this direction. So maximum radiation is perpendicular to the antenna, not parallel. Maximum radiation is always perpendicular to the antenna. Say yes or no. So this statement you can write down, or you can say that maximum radiation is at theta equals to 90 degree. Is that clear to you? But this is not always true. For Hertzian dipole, all these things are true. So you cannot call these as a fact that for any antenna your half power bandwidth will be 90 degree. For any antenna your first null bandwidth will be 180 degree, and for any antenna maximum radiation will be at theta equals to 90 degree. That means that will be perpendicular to the direction of your antenna. No, this is only true for Hertzian dipole. So what we have drawn, these are true for only Hertzian dipole, right? Now what else I can tell here? This is radiation. This I have told maximum radiation, first null bandwidth, half power bandwidth. Yeah, that's it. Yeah, one more thing, that all these things are defined with respect to E plane. This is your E plane, no? This is your E plane. Because in H plane you are simply getting a circle. In H plane you are simply getting a circle. So all these are defined with respect to E plane. So usually we will focus on E plane only. From now onwards, any antenna we study. In the next lecture we are going to study half wave dipole, full wave dipole, monopole as well we will study. Along with that we will study about quarter wave dipole, quarter wave monopole, and then 3 lambda by 2 antenna we will take, 1.25 lambda antenna we will take. So there we will only draw the E plane pattern. We will not draw the H plane pattern. Certainly H plane pattern will also be there, but we will only focus on E plane pattern, because from E plane pattern you are getting half power bandwidth, you are getting first null bandwidth, you are getting maximum radiation as well. So from now onwards we will only focus on E plane pattern. Is that clear to you? Say yes or no. So everything that we have studied in this lecture, like you can take breaks in between, but everything that we have studied, that is clear to you or not? If that is clear to you, then this question is just the summary of our complete Hertzian dipole. Complete summary it is. Every single thing that we studied and whatever that we need to keep in mind, all the things are asked. So when you revise your Hertzian dipole, this slide only you need to revise. This question you need to solve. If you are able to solve this question, if you understand every single line of this particular question, then Hertzian dipole is clear. So try solving it and don't take this question as straightforward. There is a very good thing. I am highlighting it. So try solving it and let me know the answer. I will take a break and then I will come back and then I will solve this problem. So first write down everything. What you know? AS, magnetic vector potential. You know, you know E field. You know, you know H field. You know P average. You know P radiated. You know R radiated. Everything you know. Then you can draw the pattern as well. What pattern? Radiation pattern also you can draw. So everything I have asked here. So try writing it down and let's see whether you get it correct or not. Okay, so I will take a break. I will take a pause and then I will come back. Thank you. Yeah, so let's start solving this problem. So this is in this problem every single thing that has been asked that we have studied, right? So now Hertzian dipole is there, length is lambda by 100. So length of Hertzian dipole is lambda by 100. So DL value is lambda by 100. That is given. Current value is given. Current is IT is 0.25 sin omega t. क्या हो गया यार इसको? फैन सही से नहीं चल रहा. Yeah. So this is the current 0.25 sin 10 to the power 80. Where it is placed? It is placed along x-axis, right? You need to find magnetic field, electric field at this point. R value is given, theta is 60 degree. So what is the expression of your magnetic field? H phi s. I dl sin theta upon 4 pi r sin theta upon 4 pi r into j beta e to the power minus j beta r a phi cap. Right? Now here what do we write? We write theta, and what do we say there? That theta is the angle between the arms of antenna and AR cap. This is what I say, and then I said that luckily here theta is equals to azimuthal angle only. But how do we define theta? We define theta as the angle between the arms of antenna and AR cap. Here what is the case? This is your z axis, let's just say, and this I assume as x axis. This I am calling as x axis, and this is my z axis, and my antenna is placed like this. This is how my antenna is placed. Previously my antenna was placed on z axis, and at some point r I used to find my magnetic field or electric field, whatever I used to find. Then what did I say? The angle theta is the angle between your arms of antenna and AR cap. Now at some point r there is a point P. At some distance r there is a point P, and I need to find at point P, I need to find all these parameters. This distance r is 200 lambda. They have given me a theta value, that is 60 degree. Theta value is 60 degree, but theta is the azimuthal angle here. That means this is the angle that is measured from z axis. So this 60 degree they have given, but which angle I which angle I need to put here? Which angle I put here? If I call this angle as alpha, then your alpha is the angle between arms of antenna and AR cap. Where is your AR cap? This is my AR cap, right? And where is my arm of antenna? This is my arm of antenna. So what is this angle? This angle I need to put here. Are you getting this point? Angle between the arms of antenna and AR cap. So 30 degree, this angle I need to put. Are you getting this point? Luckily, when we derived all the expression, there our theta was azimuthal angle. Along with that, it was the angle measured from the arms of antenna and AR cap. But here if I place it along x-axis, then my angle that is given as 60 degree. 60 degree is your azimuthal angle. This is not the angle between the arms of antenna and AR cap. The angle between arms of antenna and AR cap is 30 degree. So here I need to put 30 degree. A very important point, which usually students miss. So theta is already something that we define, that is azimuthal angle. But always you don't need to put theta here. Usually we remember the formula like I know dl sin theta 4 pi r j beta e to the power minus j beta r a phi cap. This is how we remember the formula. But always remember what is theta. Theta is the angle between arms of your antenna and AR cap. That is angle theta. It could be azimuthal angle as well. It could be any other angle as well. Are you getting this point? So here I need to put sin 30. So h phi s. Do I have the I naught value? Yes. Do I have the r value? Yes. Do I have the dl value? Yeah. How did I get to know that this formula I need to apply? This I got to know because of this length. This length shows that it is Hertzian dipole. Did they mention it is Hertzian dipole? Okay, they mentioned. Otherwise, if they have directly written that a dipole antenna of length lambda by 100, then also you could have told that it is Hertzian dipole only. Why is that so? Because the length is lambda by 100, which is less than lambda by 50. Length is less than lambda by 50. So certainly it is Hertzian dipole. Certainly it is your Hertzian dipole antenna. So here I am not writing it that it is Hertzian dipole. So all these formula are applicable only for Hertzian dipole. So what is dl? dl is lambda by 100. So I note I have written lambda by 100 4 pi r. Okay. Sin alpha sin 30 1 by 2. Right? Sin 30. Or here let's write sin 30. Sin 30 into j beta. Beta. What is the value of beta here? Beta is omega by Vp. What is omega? 10 to the power 8. What is Vp? 3 into 10 to the power 8. Why is that so? Because free space. Free space. Why 3 into 10 to the power 8? Because of free space. So what is the value of beta? 1 by 3. यहाँ तो आएगा ही नहीं है. J into 1 by 3 e to the power minus j beta r a phi cap. Here they are asking me the magnetic field expression. They are asking magnetic field expression. So they are not only asking the phasor form, they are asking the complete expression. Okay, just a minute. Yeah, sorry for the interruption, one call came in between. So yeah, now I need to solve all this. Okay, so lambda will get cancelled. Sin 30, you know, it is 1 by 2, this is 1 by 3 only. So when I solve it, 0.25 into 1 by 2 into 1 by 3 divided by 4 pi divided by 200 divided by 100. So when I solve all this thing, what I am getting is that I am getting 1.65 into 10 to the power 1.65 into 10 to the power minus 7. Okay, and then there is j, and then there is e to the power minus j beta r. So what is the value of beta? That is 2 pi by lambda. And what is the value of r? R is 200 lambda. R is 200 lambda. Yeah, one more thing, r is equals to 200 lambda, which is greater than lambda by 6. That's why it is your far field. And if it is a far field, that's why we can apply these expression, right? So it is a far field. Certainly if the question is coming, that will be based on far field only, but you need to verify it that this is a far field, right? So what we are getting? So 1.65 into 10 to the power minus 7 j e to the power minus 400 pi. What is the value of this? 1. And certainly there is a direction as well. So let's not cancel lambda to lambda, and this is the direction. So what is the value of this one? What is the value of this thing? That is 1, right? Cos 400 pi plus iota sin 400 pi. Cos 400 pi plus j sin 400 pi. Sin 400 pi is 0. So cos 400 pi is 1. So that is 1. So this value is 1. So what you are getting? 1.65 into 10 to the power minus 7 e to the power j pi by 2. This is your h phi s. But wait a minute, this is the phasor form. My phasor form is h phi s is 1.65 into 10 to the power minus 7 e to the power j pi by 2. This is the phasor form. Now I need to go to the time harmonic vector field. If I need to find time harmonic vector field, what I will do? I will add up e to the power j omega t. Then either I will take real part or I will take the imaginary part. Certainly there is a direction as well. So either I will take the real part or I will take the imaginary part. Now you just let me know whether I will take the sin theta, whether I will take the sin part or cos part. What do you think? I will take the sin part. Why is that so? Because I need to look at the current source. What is my current source? My current source is sinusoid. So if you remember, when we got our AS expression, let's get back to the derivation. When we get this expression, I assume that it is coming from here. Like my I was I naught cos omega t minus beta r, then I took the phasor. So from here to here, if I need to go, from phasor to time domain form I need to go, I will put cos only. Because I got my phasor from here now. Like if I need to go from here to here, from phasor to time domain form if I need to go, from phasor to time harmonic vector field if I need to write, then what I will pick? I will pick the cosinoid term. No, I will not pick sinusoid. Because my current expression was cosinusoid. And using this expression we got other expression. From using this expression we got other expression. So if in my question, if my current source is cosinusoid, then my final answer will also be in cosinusoid only. But if my current source is sinusoid, then my final answer will be in sinusoid only. So all depends on the current source. So till this point I did all the calculation, but now if I need to write down the time function, So that will be, I can write down 0.165 cos, not cos, sorry, sine omega t plus pi by 2 a phi cap. And why I have written sine? Because my current was 0.25 sine. So always when you need to write sine or cosine, that you will decide with respect to the current source. So that's why here I wrote sine, because from here you will get your e to the power minus j beta, right? Because in the 10 to the power 8, what you are going to do? T minus t naught. So from there you will get t minus t naught value you will put, and from there you will get your e to the power minus j beta. So when you are going from back from here to here, then you need to put a sinusoid. Is that clear to you? So this is how we will decide whether we need to take real part or the imaginary part. So here I am taking imaginary part. And another thing, if I am writing all this thing, then the final answer will be microampere per meter. Microampere per meter. So this is my H phi component. What about E? E will be in the direction of theta, right? What different would be there? It will be multiplied with 120 pi. So it will be multiplied with 120 pi. So 0.165 into 120 into pi. So 62.20 sine omega t plus pi by 2 a theta cap, and that would be microvolt per meter, right? What here we have done is that E naught is equals to neta H naught. So this we have find out. What else they are asking us to find out? Power radiated. So for P radiated, what you know, that is equals to I naught square by 2 into R radiated. What is the value of R radiated? R radiated is 80 pi square dl by lambda whole square under root mu r by epsilon r. These are one only. So what you are getting? R radiated equals to 80 pi square. What is your dl? Lambda by 200, lambda by 100. Lambda by 100 into lambda. So 80 into pi divided by 100 and divided by 100. So you are getting 78.9 milli ohm. 78.95 milli ohm. 78.9 milli ohm. And now if I need to find P radiated, that would be I naught square by 2 into R radiated. And what is your I naught? 0.25. It was 0.25 only, no? Yes. So 0.25 whole square divided by 2 into 78.9 milli. So what we are getting? Into 0.25 into 0.25 divided by 2. And if I do 1000, then I am getting 2.46 milliwatt. I hope the calculation is correct. Let me do the calculation again. 80 into pi whole square divided by 100 divided by 100 into 1 by 16 by 2. 2.46 milliwatt. This is your P radiated. So power radiated you have find out. What else they are asking? Draw its field pattern and find the position of nulls. So field pattern we will draw. Now find the phasor form of magnetic vector potential, or you can write down complete magnetic vector potential as well. No need to write down the phasor form. If I need to write down the phasor form, what I will write down? So mu ideal sin, not sin theta, mu ideal upon 4 pi r e to the power minus j beta r, and here direction will be ax cap. Why is that so? Because your antenna is placed like this. In the direction of x-axis it is placed. So your antenna is placed like this. So this is your current. So current is in AX gap. Is that clear to you? So what is the value of mu naught? 4 pi into 10 to the power minus 7. Since it is free space. And here it's not I, it's I naught. So 0.125 into lambda by 100. DL is lambda by 100. This is also 4 pi lambda by 100, and this is 200 lambda e to the power minus j. This is 400 pi and AX cap. Is that clear to you? So no need to write down phasor form. I will just say find the magnetic vector potential. No need to write down the phasor form, because phasor form is very easy, but the complete magnetic vector potential we will find out. So what you are getting? Mu ideal 4 pi r e to the power minus j beta r AX cap. So let's do this calculation. This will be 1 only. This is 1. So only calculation is left, that is 0.125 divided by 100 divided by 200. So 6.25 into 10 to the power minus 6. Nothing is left, no? This is 10 to the power 3, 10 to the power minus 7. 10 to the power minus 7, 6.25 into 10 to the power minus 6, and then this would be 6.25 into 10 to the power minus 13 into 10 to the power minus 13 Weber per meter AX cap. But this is the phasor form only, no? This is the phasor form you have written. AX cap, this is the phasor form. If I need to write down the time domain form, what I need to do? If I need to write down that time domain form, so I need to multiply e to the power j omega t. Yeah, the unit is Weber per meter. You need to know it. Okay, unit is Weber per meter. Here it is ampere per meter. No, for H it is ampere per meter. So here it is Weber per meter. Okay, and I hope the calculation is correct. 10 to the power minus 3, 10 to the power minus 4, 10 to the power minus 7. This will be 62.5 only. This is 62.5, not 6.25. No, 10 to the power minus 3, 6, 62.5, 10 to the power minus 7. Yeah, 6.25, 10 to the power minus 13. Yeah, that is correct. So 6.25, 10 to the power minus 13, e to the power j omega t AX cap. Now if I need to take the real part or imaginary part, which part I will take? Because of the sinusoid here, I will take the sinusoid part. Sin omega value you already know, 10 to the power 80 AX cap. So this is your complete expression of your magnetic vector potential. So people think that these complex expression will not be asked in the examination, and then they ignore. Now what if I give you the same question and I frame 4 options like this, and certainly unit is Weber per meter. So I can frame 4 options there. So what you will do there? There you need to remember this formula, no? This formula should be there. This formula you should remember. So all the things that you need to remember, everything has been asked in this question. This formula you need to remember. This formula should be there in your mind. You need to know the meaning of theta. So everything is asked in this question. Now you need to draw the radiation pattern. Radiation pattern. Make sure what is your normalized value of E here. Normalized value of E. What do you think? What will be the normalized value of E? That is sin theta, no? But what is theta? Theta is the angle measured from. Theta is the angle. Here you write theta. So that angle is the angle between the arms of antenna and AR cap. This is my Z axis. This is my X axis. And this is my antenna. अच्छा ही नहीं बन रहा यार, फिर बुक गिरेगा. This book doesn't stay here. These books keep on falling. Yeah, so here if I need to define the angle, so this is your theta, this is your theta, but here I'm not gonna write theta. Here what I will write now, 90 minus theta. No, are you able to understand? Because here my field pattern, forget about it, you are getting confused here. So if I write down the complete E expression, E theta S expression, if I write down the complete E theta S expression, what that would be? Neta into ideal sin theta upon 4 pi r, and here in place of sin theta what I will put? Sin alpha. And what is alpha? Alpha is 90 minus theta, because you know that what is the angle, what is the angle that we put here? That is the angle between the arms of antenna and AR cap. So 90 minus theta, and then e to the power minus j beta r, also there will be j beta as well, and then a theta cap. This will be the complete formula. No, so if I calculate the normalized value of E, so what I need to do, I need to eradicate all these things. So only what will be left? Sin 90 minus theta. Sin 90 minus theta. What that would be? Sin 90 minus theta is cos theta. This is your normalized value of E. And if I need to find the nulls, if I need to find the nulls, so what I need to do? So cos theta is equals to 0, so that you get at 90 degree only. So your null is at 90 degree. So this is the location of your null. And can I draw the pattern now? So what I need to do? I need to draw En versus theta for phi equals to 90 degree, and this is known as E plane, right? So let's draw it once. So E plane means which plane? YZ plane. Which plane? YZ plane, right? E plane is YZ plane. This is your Z, this is your Y. Where is your antenna? Your antenna is here. Your antenna is here. Here is your antenna, because that is placed along x-axis. No, antenna is placed along x-axis, and your E plane is your YZ plane. Are you getting this point or not? Right? I hope you are understanding this point. E plane is my YZ plane, that you know, elevated YZ plane, and antenna is placed along x-axis. So, and this is my antenna. This is my antenna. And here taking angles, like I need to take different angles. It could be 0 from 0 to 180 degree. I need to take angles, and then I need to draw the graph of cos. So this is my theta equals to 0 degree. This is my theta equals to 90 degree, and this is my theta equals to 180 degree, right? And this is my theta equals to 90 degree only. So at 0 degree you are getting the maximum value, because cos 0 is 1, cos 0 degree is 1, cos 45 degree is 1 by under root 2, and cos 90 is 0. So here you are getting maximum, then this value, and then this value. So kind of this pattern you will be getting. Kind of this kind of pattern you will be getting, and similarly here as well. Here I made it better. Similarly here as well, and same goes for this as well. Downward as well you will get the same, because what is cos 180? What is cos 135 degree? Cos 135 degree, that is minus 1 by under root 2. Actually that is negative, but only positive value we will take. Positive value only we will take. And what about cos 180? That is minus 1, but we will take the magnitude only. What we will take? We will take the magnitude only. So this thing I forgot to tell. Here it will be clear that we will take magnitude. So we will take magnitude. At 135 you are having again the same thing. At At 90 degree you are having 0, at 135 you are having 1 by root 2, and 180 degree you are having the maximum, and same goes here as well. So this kind of pattern you are getting. This kind of pattern you are getting, right? Now in the examination what may happen is that here they can make x-axis as well. What I mean to say is that in the examination, in one of the option, what kind of pattern you can get? In the examination, in one of the option, you can get this kind of pattern as well. What kind of pattern? What they will do is that here they will mention x-axis and they will place the antenna like this. They will place the antenna like this. That antenna is placed like this. And now they will not show it z-axis or anything. They will not show you z-axis or anything. They will just tell that this is your theta equals to 0 degree. This is your theta equals to 90 degree. This is your theta equals to 180 degree. They can write it down 270 as well. Sometimes we have seen that in some of the textbook this is written as 270 as well. But you don't need to worry. You will just know this thing that these will be symmetrical. So 270 you can keep as 90 only. So what you will do? You know that this is my normalized value. And certainly I need to take the mode. Okay. So at 0, what I am getting, cos 0 is 1. Then 45 degree 1 by root 2, and then again here is 0. So at x-axis as well, theta will be equal to 90 degree only, no? At x-axis, this is my z and this is my x. Here I am showing it. This is my z and this is my x. This is my 0 degree. So in x-axis as well, it will be 90 degree. If you remember this diagram, this diagram I showed. So if I call this as my z-axis, this as my x-axis, and this as my y-axis. So this is your theta equals to 0 degree. This is your theta equals to 90 degree. Similarly, this is also theta equals to 90 degree only, no? Are you getting this point? From z to x you come, or from z to y you go. This is also 90 degree. So here I am not saying whether it is E plane or H plane. I am not mentioning it. Whether it is my E plane or H plane, nothing I am mentioning it. I just told this thing that, sir, this is theta equals to 90 degree. This is theta equals to, this is theta equals to 0. This is 90, this is 180, and this is again 90 or 270 you can write down. And my antenna is placed along x-axis. That means certainly it has to be theta equals to 90 degree. Because antenna is placed along x-axis. So now I can draw my pattern and it will be same. It will be same as before. Because the values are same. On the axis values are same. So it will be same as before. Forget about it. I will draw the circle only. I will draw the circle only. There you go. So this looks more intuitive, like you can see here that at the perpendicular direction from the antenna there is maximum radiation. From the antenna at the perpendicular direction there is maximum radiation. Here also it is same. The maximum radiation is perpendicular only. Because what is this axis? This axis is minus z. And what is this axis? This axis is x axis. So you are getting your maximum radiation at minus z. That means that is perpendicular only. So here also you are getting maximum radiation in perpendicular direction only. But here if I make it on xz plane. So this I have made on E plane. But here this is not any specific plane. I cannot call it E plane. But one thing for sure, that in xz plane this is how it will look like. And in xz plane this will be the value of theta. 0 degree, 90 degree, 180 degree and 90 degree. Say yes or no. Did you understand this point or not? This is x, this could be minus x. This is z, this could be minus z. So here 0 to 180, 90 to 90. This is 90 and this is also 90. And this is how we can draw it. If your coordinate system is clear, then you will be able to understand. Otherwise you will not be able to understand. So you can invest 2 hours in studying spherical coordinate system first and then come back here. No matter from wherever you have studied, please once study spherical coordinate system from our channel as well. So you will realize a lot of things are there and great intuitive things you will learn there. Okay, so yeah, this is the not standing wave pattern, this is the radiation pattern. And we are not going to draw that H plane pattern. That is pretty obvious that how H plane pattern will look like. That would be a circle only. So that we don't need to plot. Okay, so That H-plane pattern, forget about that H-plane pattern. So E-plane pattern we have drawn. This is how the radiation pattern will look like. And if the question is coming in the examination, then this pattern only will be made. And where there is very high chance that they will put your antenna on horizontal axis. They will not put antenna like this. Although they can put like this as well, but mostly chances are there that antenna will be put like this. Because from here you get to know that in the perpendicular direction there is maximum radiation. In the perpendicular direction there is the maximum radiation. And radiation is there on both of the sides, ahead of antenna and the back of antenna as well. Right? This is how it will be plotted. So yeah, that's it. That's it about our complete lecture on Hertzian dipole. So now next dipole will be just a cakewalk for you, because everything you have studied in Hertzian dipole in a very good manner. So now we are going to study about other dipoles like half wave dipole, full wave dipole, quarter wave dipole, monopole also we will study, and then we will see their radiation pattern as well. And from now onwards we will always discuss about E-plane only. Okay, so E-plane pattern only we will discuss. Or what we are going to do, forget about E-plane. We will always take our antenna on horizontal axis. What we are going to do, we will take our antenna on horizontal axis, and with respect to that we will define the values of theta. Our antenna is placed on x-axis, so this value will be 0 degree, 90, 180 and 90. If it was placed on z-axis, then this would be 0 degree, this would be 90 degree, this could be 180 degree and this would be 90 degree. So in that manner we will define. Is that clear to you? So I hope you enjoyed the lecture of this Hertzian dipole. I know things are not that straightforward, but I cannot teach you things on surface level. I am never going to teach things on surface level. I need to go into the depth of the concept. So I hope every single thing, every single concept is clear regarding our Hertzian dipole. And this question is just for the revision, that if you solve this question, that means you know everything about Hertzian dipole. You need to remember the H5x expression. You need to remember E expression. You need to remember P radiator expression. You need to remember AS expression as well, magnetic vector potential of phasor form, that also you need to know. And then you need to write down the time domain form as well. How will you write down the time domain form? Whether you will pick sine or cos, that is depending on the current source. And in that manner you need to see this is the radiation pattern, how to draw the radiation pattern, that also we have studied. So for any random antenna you can draw the radiation pattern. What you need to do, you just need to write down the normalized value of electric field. If you are able to write down the normalized value of electric field, then that's it for you. And simpler way is, whatever the angle term you can see, that term you need to pick, that will be your normalized value. And also you need to see that what is your angle theta. Theta is not always the azimuthal angle, it could be anything. It is actually the angle between the arms of antenna and AR cap, right? So yeah, that's it about our lecture 2, that is based on Hertzian dipole. In the next lecture we are going to see more kind of linear dipole antenna. Thank you very much.